All right, let's dive into some four-dimensional topology.
Yeah, sounds good.
Today we're looking at KOUICHI YASUI's paper, Corks, exotic four manifolds, and genus functions.
Great paper.
This paper is really something else. It's packed with theorems and definitions
Oh, yeah.
that could make your head spin. But don't worry,
Yeah,
we've got our expert here to help us navigate the complexities.
I'll do my best.
So let's jump right in.
Okay.
The core concept here is genus functions. They sound kind of biological,
Right.
but I have a feeling they're anything but simple in this context.
You're right. They're not simple at all. A genus function is a really powerful tool that helps us understand
Okay.
the different smooth structures that a four-manifold can have. It's like a mathematical fingerprint.
Okay.
It captures subtle geometric information that can help us distinguish between these exotic structures.
So you're saying we could have manifolds that might look the same topologically,
Yes.
like having the same number of holes.
Right. Yeah.
But when you zoom in on the smooth structure, they're fundamentally different.
Exactly. And that's the beauty of genus functions.
Okay.
They let us quantify these differences, even though it's impossible for us to
Yeah.
visualize these exotic structures directly.
Okay, now that's where my brain starts to melt a little.
Yeah.
But that's what we're here for, right? To
That's what I'm
explore
here. Excellent.
these mind-bending realms of higher dimensions. So Yasui starts off by discussing
Right.
different types of equivalences between genus functions. What's the significance of that?
Oh, that's important because these equivalences tell us how much information about the smooth structures is actually contained in the genus function. We have ordinary equivalence, oriented equivalence, and algebraic equivalence.
Okay.
Each of these corresponds to different types of transformations, things like
Yeah.
homeomorphisms and diffeomorphisms. These transformations preserve certain aspects of the manifold structure.
So it's not just a yes or no.
Right.
There are shades of equivalence
It is
that can
indeed
reveal
so.
different levels of similarity between these exotic structures.
That's a great point. It's pretty subtle.
Yeah, it is.
And this subtlety is what makes the study of smooth structures so fascinating.
Okay.
Early on in the paper, Yasui highlights in Proposition 2.6
Okay.
that for certain types of four manifolds, like rational surfaces and blow-ups of ruled surfaces, the genus function can actually completely determine the smooth structure, at least among symplectic four manifolds.
Now, you mentioned symplectic four manifolds.
Yeah.
Did you elaborate on what those are and why they're so important in this context?
Sure, symplectic four manifolds have this special geometric structure.
Okay.
It's called a symplectic form, and it's a closed, non-degenerate two form.
Okay.
Basically, you can think of it as a way to assign an area to any two-dimensional surface within the manifold.
Interesting.
This structure is super important in tons of areas of math and physics,
Okay.
especially in studying Hamiltonian mechanics.
So it's like these manifolds
Uh-huh.
have this inherent sense of area that's deeply tied to their geometry and dynamics.
Precisely. And for these symplectic four manifolds,
Okay.
if you know the genus function, it can unlock the secrets of their smooth structure, which is really quite remarkable.
It is pretty amazing.
Yeah.
But I have a feeling that things are about to get even more complex
Of course.
as we dive deeper into the paper.
Qualities.
So next,
Right.
Yasui introduces this concept of corks,
Yes.
which are really important for understanding how to build exotic four manifolds.
Right.
Corks,
Yeah.
like what you find in a wine bottle.
Yeah, like in a wine bottle.
What do those have to do with four-dimensional topology?
Well, it is a kind of funny analogy,
Yeah.
but it does actually capture the core idea.
Okay.
These corks are special four-dimensional building blocks,
Okay.
and you can embed them into a manifold. And here's the crazy part.
Okay.
When you do something called a cork twist, it's basically a specific type of surgery on the manifold.
Oh, wow.
It actually changes the smooth structure of the manifold without changing its underlying topology.
Hold on. So we're saying you're changing the fundamental smooth fabric
Yeah.
of the manifold
Yes.
while keeping its overall shape intact.
Exactly. It's like doing this subtle surgery that changes the internal structure
Okay.
without changing what it looks like from the outside. And it's this ability to manipulate these smooth structures using corks that lets us build these exotic four manifolds.
Wow. That's where things start to get truly mind-boggling.
I know.
So these corks allow us to create exotic structures. But how common are these exotic structures? Are they rare?
good question.
Or are they more widespread than we might think?
Well, that's a key question that Yasui looks at.
Yeah.
In Theorem 3.4, he proves that any four-dimensional two-handle body, as long as it has a certain type of hole, can be modified using cork twists to have any number of distinct exotic smooth structures.
Wow. So you're telling me we can take a four-dimensional shape with this specific type of hole and using these cork twists create an infinite variety of exotically smooth versions of it.
You got it.
That's incredible.
Yeah.
It's like we're unlocking these hidden dimensions within the smooth structure itself.
Yeah, it's pretty wild.
And the method behind this is just as fascinating as the result itself. So Yasui carefully constructs these cork twists. And he combines them with other modifications like W modifications to create these exotic structures while making sure that certain properties of the original manifold stay the same.
Exactly.
So it's not just random twisting.
No, not all.
There's a precise method to the madness.
It's very precise.
So there's a method. And this leads us to the idea of infinite order generalized corks. Which really takes this idea to a whole new level. Infinite order. Sounds powerful. It is pretty amazing.
So what exactly are these generalized corks?
Well, think of them like supercharged corks. When you twist an infinite order generalized cork, you don't just get a handful of new smooth structures. You get an infinite number of them.
Wow. So we're talking about infinite smooth possibilities from a single cork twist.
Exactly.
That's really mind-blowing. So are you saying that exotic structures aren't just possible? They're potentially abundant?
They are.
In 4 dimensions?
It seems that way.
Wow. And Theorem 4.1 makes it even more incredible. It states that you can modify any 4-dimensional two-handle body to become an infinite order generalized cork.
That's right.
In other words, the potential for infinite exotic variation is basically lurking within almost any 4-dimensional shape that we can imagine.
Pretty cool.
That's a profound thought. It completely changes our perspective.
On what 4-dimensional space is all about. It's not just about the shapes themselves.
It's so much more.
It's about the infinite potential.
That's amazing.
For these exotic smooth structures hidden within them. But how do we even begin to grasp
It's tough.
this vast landscape of exotic possibilities?
That is the question. And that's where the next part of the paper comes in. Yasui digs into how these exotic structures affect the stability of these genus functions. And he looks at the tools and techniques that we can use to analyze them and try to classify them. And we'll see how attaching these special 4-dimensional connectors, which are called cobordisms, can either preserve or change these genus functions. This gives us some really interesting insights into the relationships between different smooth structures. So get ready for some even deeper dives.
All right. I'm ready into this world of 4-manifold.
Buckle up.
Okay. So last time we were talking about how these exotic smooth structures affect the stability of these genus functions. And you mentioned attaching cobordisms. Which sound like bridges between manifolds.
That's a good way to think about it. They are like bridges that connect different manifolds. And Theorem 7.1 in the paper shows something really cool. Attaching a certain type of cobordism called a quasi-invertible cobordism actually keeps the genus function the same.
Wait, so you're saying we can attach this bridge to a 4-manifold, change its shape and structure, and its fingerprint, the genus function stays the same.
Exactly. It might seem counterintuitive.
Yeah, it does.
But that's what makes it so interesting. This means we can build these complex 4-manifolds from simpler pieces using these quasi-invertible cobordisms as connectors. And we can maintain control over their genus functions.
So it's like we have this delicate 4-dimensional Lego set.
I like that now.
Where we can attach pieces without changing the fingerprint of the whole structure.
Exactly. It's a great way to think about it.
Okay, so what else does Yasui tell us about the stability under cobordism attachments?
He goes deeper into specific scenarios. Where the genus function stays stable. For instance, theorems 7.7 and 7.8. Look at even more specific conditions for genus function stability. They show us that by carefully choosing which cobordisms to attach and how to attach them, we can either keep the genus functions the same or control the small differences that come up.
So it's not just about attaching any cobordism.
No, it's not.
It's about making strategic choices.
Right.
That either maintain or predictably alter the genus function.
Precisely. It's like a set of rules for how to combine these four-dimensional building blocks to create structures with the properties that we want.
It sounds like conducting an orchestra.
Yeah, kind of.
Or composing these exotic four manifolds.
That's a good way to put it.
Using these cobordism connections.
I really like that.
But what happens when we go beyond attaching cobordisms? What happens when we actually start merging manifolds together?
That's where things get even more interesting. Yasui explores that too. He looks at connected sums and boundary sums. These are two common ways to glue manifolds together. For example, theorem 8.4 shows that if you take the connected sum or the boundary sum of a manifold with a submanifold of a specific type of surgered four-manifold, it actually keeps the genus function the same.
Hold on. So let me make sure I understand. We're taking two manifolds. Maybe with different genus functions. And we're gluing them together using these connected sums or boundary sums. And under certain conditions, the new manifold gets the genus function of one of the original pieces.
That's right. It's like one of the genus functions wins out over the other, even though we're merging them together.
And this happens when we use submanifolds of a certain type of surgered four-manifold, which have their own special properties.
So many technical details.
Yeah, four-manifold theory is full of
It's like a game with all these intricate rules.
That's a good way to look at it.
But the payoff is incredible. You get these amazing insights into the structure of four-dimensional space.
Absolutely. It also keeps going. It gives us even more refined results. Like theorems 8.7, 8.9, and 8-point sums. These look even deeper into stability of genus functions under these sums. They show how to build complex manifolds while still keeping control over those algebraic properties of their genus functions.
So we're building up a whole family.
In a way, yes.
Of manifolds, from the simple to the complex. And we're figuring out how their genus functions interact and change as we combine them in all these different ways.
Exactly. It's like creating a family tree.
Of manifolds and tracing their lineage to see how their properties are passed down and modified.
But I bet there are some surprises waiting for us.
You bet. There always are.
In the world of four-dimensional topology.
Especially there. Remember how we were talking about genus function being this unique fingerprint that helps tell smooth structures apart? Well, Yasui reveals something really shocking.
What's that?
There are actually cases where completely different exotic four-manifolds can actually have the exact same genus function.
Wait a minute. That's like saying two different people can have the same fingerprint.
I know. It's crazy, right?
Doesn't that mean that the genus function can't always tell the difference?
It does mean that.
Between smooth structures.
It does.
This is not a perfect identifier.
It's not perfect, no. But it highlights just how complicated four-dimensional topology really is. Theorem 9.5 in the paper actually states this result. For any four-dimensional two-handle body, you can create a countless number of exotic four-manifolds. And they all have the same genus function.
My mind is blown. So you're telling me we can have all these completely different smooth structures. But their fingerprints look identical.
Exactly.
How is that even possible?
It's amazing. It shows us that genus function doesn't tell us everything about smooth structure. There are things about these exotic manifolds that genus function just can't see.
So it's like we need a stronger magnifying glass. A better set of tools.
We need better tools for sure.
To explore these hidden depths and separate these exotic structures that all have the same fingerprint.
It's a huge challenge.
And that's where the exciting stuff comes in, right?
Absolutely. The search for new invariants, ways to characterize these exotic four-manifolds, that's a hot area of research. We're at the edge of a vast unknown territory.
It sounds like it.
And Yasui's work gives us a glimpse of what we might find.
So if genus functions can't fully distinguish these exotic structures, what other paths can we explore?
Well, Yasui gives us some hints. He mentions theorem 9.7 briefly, and it shows this really intricate relationship between genus functions and exotic structures. Just imagine infinite families of exotic manifolds, each with its own distinct genus function. But here's the twist. Within each family, the genus functions are all equivalent.
So it's like we have these different families, each with its own unique set of fingerprints, but within each family, everyone shares the same prints.
Mind-blowing, isn't it?
That's a crazy level of organization. Within this world of exotic structures.
It suggests there's a hidden structure that governs these exotic manifolds that goes beyond what we can see at first glance.
It sounds like we're piecing together this grand cosmic puzzle.
It does feel that way.
Where each clue reveals a little bit more about the structure of four-dimensional space.
And Yasui, with his theorems and results, he's our guide in this incredible journey.
I'm ready to see what other pieces of this puzzle
Me too.
he reveals.
Let's see what he's got.
Okay, so we've gone pretty deep now.
Yeah, we have.
Into this world of exotic four manifolds.
It's fascinating stuff.
And we've explored the strengths and weaknesses of these genus functions. And we've even caught a glimpse of this hidden structure within these seemingly chaotic structures.
Yeah, it's pretty mind-blowing.
So where does Yasui take us next?
Let's see.
In our exploration of this mind-bending landscape.
We'll get ready for even more surprises. Yasui digs deeper into what these exotic structures mean for our ability to tell four manifolds apart, even when we have lots of information about them.
So you're saying even with all the tools we've talked about, there are still times when we can't be completely sure
That's right.
if two four manifolds are actually different.
Exactly. And theorem 9.9 shows us that even if two closed four manifolds have the same cohomology ring, which basically tells us about their algebraic structure, and even if they have really large second Betty numbers, which means they have lots of those two-dimensional holes we talked about, we still might not be able to tell them apart.
Wow, that's a bit unsettling. It's like looking at twins.
Yeah, I know what you mean.
With the same DNA. And not knowing for sure if they're truly different.
It really shows us the challenge of understanding these higher dimensional spaces.
So does this mean our tools are just not good enough?
It could be.
To really understand four-dimensional topology?
It might be that we need new tools. New ways of looking at things. The genus function is great, but it's clearly not enough. We need new invariants. New ways to describe and classify these exotic four manifolds.
So the search for new tools is really important.
It's essential.
In four manifold theory. But where do we even start looking for these new insights?
Well, Yasui gives us some hints. He mentions theorem 9.7, which shows this really intricate relationship between genus functions and exotic structures. Picture this. We have countless families of exotic manifolds. Each family has its own unique genus function. But here's the crazy part. Within each family, all the genus functions are the same.
So each family has its own fingerprint.
Exactly.
But every member of the family shares that same print.
It's wild, right? It points to this deeper level of organization that we're only beginning to understand.
It's like a detective story.
It kind of is.
We're piecing together these clues to uncover this hidden world.
It's a good analogy.
Of four-dimensional topology. And Yasui's our guide.
That's right. He's leading the way.
Through this amazing mystery, what other clues does he give us?
Well, he ends the paper with a bang. He shows us that we can not only observe these exotic structures, but we can actually create them.
Oh, wow.
Theorem 1.17 proves that we can build these families of Stein four manifolds. Remember, those are the ones with that special symplectic structure. Well, when you combine these Stein four manifolds, you always get exotic structures.
So we're not just watching these exotic things happen.
Nope.
We're actually making them happen.
Exactly. We're like chefs in the kitchen, cooking up these mind-blowing exotic structures.
It's amazing how we started with
I know, right?
this abstract idea of genus functions and ended up in this world
It's quite a journey
of exotic four manifolds.
It is.
With all their hidden structures and surprising connections.
And don't forget the ability to create them ourselves.
It's really remarkable. It shows the power.
It does.
And the beauty of mathematics.
For sure.
Well, I'm feeling pretty amazed.
As you should be.
After this deep dive.
It's inspiring stuff.
It's exciting to be at the edge of what we know.
I agree.
Exploring the unknown.
Yeah.
And asking these questions.
It's what it's all about.
That push the limits of what we can understand.
Absolutely.
That's the beauty of math.
Right.
It's a never-ending adventure.
It never gets old.
This constant search for knowledge and truth.
And every new discovery opens up new questions and mysteries.
It's incredible.
It is.
Well, I think it's time to wrap up this deep dive. But before we go, I want to leave our listeners with something to think about.
Shoot.
If genus functions can't completely distinguish these exotic, smooth structures, what other things might we need?
It's a good question.
To unlock the secrets
of
four-dimensional topology.
It's something to think about.
What new math will we need to create?
We need new tools.
To truly map out this uncharted territory. Let us know what you think. We'd love to hear from you. Until next time, keep exploring and keep asking questions. See you next time. Welcome to the Deep Dive. Today, we're going deep into exotic, smooth structures on four manifolds and their genus functions.
Oh, yeah.
And we've got a fantastic guide for this. It's KOUICHI YASUI's paper, Corks, Exotic Four Manifolds and Genus Functions.
Great paper.
So yeah, get ready for some pretty advanced math.
It's going to be fun.
Yeah. And right away, the title kind of hits you with this mind-blowing concept. Is, infinitely many exotic, smooth structures.
Right.
All in a single four manifold.
Yeah.
It's like, how can a space look the same topologically, but be completely different smoothly?
Yeah, that's where this whole idea of like exotic smooth structures comes in.
Okay.
You can think about it like, imagine you have two sculptures. They look identical, but at a microscopic level, their surfaces are totally different. That's what's happening here. These exotic four manifolds, they have the same topology underneath, but they're different in their smooth structure. That's like how you can move on the surface smoothly.
Gotcha. Okay, so to make things even more interesting, Yasui's focused on four-dimensional two-handle bodies.
Yeah.
So these are basically four manifolds built by attaching these handles to a zero handle. Like imagine building with Legos, but instead of bricks, you've got these higher dimensional handles to create like loops and twists.
Yeah, exactly. These two handle bodies are like the fundamental building blocks in this whole theory of four manifolds.
Yeah.
And Yasui's theorem 1.2, it's really something. It says any four-dimensional two-handle body, you can actually modify it to have infinitely many exotic smooth structures.
Ooh.
It's wild. And there's more. All these structures, they have equivalent genus functions.
Okay, wait, hold on. Genus functions?
Yeah.
That sounds pretty sci-fi.
Yeah.
What are those? And like, why are they so important here?
So, picture this. You've got a surface, like a sphere or a torus, and it's sitting inside our four manifold. The genus function, it measures how complex this embedding can be. Basically, it tells you the minimum number of holes the surface needs to represent a specific second homology class. So if you have two four manifolds and they have equivalent genus functions, it means that surfaces can embed in a similar way, even if their smooth structures are different.
Wow, so even though they're smoothly distinct, they have a similar feel topologically.
Yeah.
In terms of how surfaces fit inside, that's kind of counterintuitive.
Right. And this leads to some really surprising results. Take corollary 1.3, for example. Yasui shows that for any integral symmetric bilinear form, we can actually find infinitely many exotic, similarly connected four manifolds, and they have equivalent genus functions. And their intersection forms, they match that specific form.
Whoa. So these exotic structures are way more common than we might think.
Yeah.
It's crazy to think there could be like infinite versions of these spaces all kind of hidden from our usual view, like you've got a room full of identical twins, but they're all totally different on the inside.
Yeah, that's a great analogy. It shows how powerful smooth structures can be. They reveal a whole level of complexity that goes beyond just what we see topologically.
Absolutely. So are there any four manifolds where the genus function actually determines the smooth structure? Like, are there any spaces where there's no room for these exotic variations?
There are, actually. Yasui's proposition 2.6, it zooms in on some familiar spaces like rational surfaces, things like CP2 tag in CC2,
right,
or blowups of ruled surfaces. He shows that for those, the genus function actually locks in the smooth structure, at least if we're talking about symplectic four manifolds. So for those specific types, the genus function is like the key to unlocking their smooth secrets.
Interesting. So in those spaces, smooth structure is totally tied to how surfaces can embed within them.
Yeah.
But I guess the big question is, how does Yasui actually create these exotic structures in the first place? Like, what's his secret weapon?
His secret weapon is Corks.
Corks? Yeah. It's like this tiny, contractible, four-dimensional bubble, and it has this really unique property. On its boundary, there's this special self-homeomorphism that you can't smoothly extend to the whole cork. These corks are super interesting on their own.
Yeah.
And Yasui uses them to build exotic structures. He does it by twisting them inside bigger four manifolds.
Okay, I'm trying to picture this. So like little 4D bubble, and you're twisting its surface so it gets stuck inside.
Right. And the amazing thing is that cork twist, it changes the smooth structure of the whole four manifold, but it doesn't change the topology. It's like doing surgery on the smooth structure, leaving the overall shape the same, but changing how it works at a fundamental level.
That's wild. So by strategically placing and twisting these corks, Yasui can create these exotic variations. It's like some kind of four-dimensional origami where you're folding and twisting space to make these new structures.
Yeah, that's a great way to think about it. And Yasui takes it even further in theorem 3.6.
He uses these things called invertible homology cobordisms to build even more complex exotic four manifolds from what he calls generalized corks. Think of these cobordisms like temporary four-dimensional bridges. You can attach them to a manifold, twist things up, and then detach them.
So you're left with
a brand new exotic structure.
I see. So he's like a master builder. Using corks as his special pieces in these cobordisms to connect everything.
Exactly.
And the theorem says the manifolds he gets are actually different and exotic.
That's right. He even gives examples, Gomp's infinite order corks. He uses those to show how powerful this technique is.
Yeah.
And for people who like visuals, there's a diagram of these corks in figure 2 of the paper.
Cool. I like visuals. So theorem 4.1, that seems like a big deal. It says that you can take any four-dimensional two-handle body and turn it into an infinite order generalized cork. So these structures aren't rare, they're everywhere.
Yeah, they're all over the place. And proposition 4.2 gives us a more hands-on way to build them. By embedding the four manifold into a symplectic four manifold with a weakly convex boundary, it opens up a whole new way to explore these exotic four manifolds.
This is incredible. Yasui's basically revealing a hidden universe of exotic structures.
That's amazing.
Right under our noses.
Yeah.
But how does all of this connect to, like, knots? I keep thinking about how twisting these corks is like tying knots.
You're onto something there. Theorem 1.9 links those ideas together. It says that under certain conditions, you can take any codimension 0 submanifold and modify it into infinitely many exotically knotted versions. So picture a simple sphere sitting inside a four manifold. Yasui's saying you can knot it in ways that are totally impossible in our usual three-dimensional world.
So there are like infinitely many knotted versions of a simple sphere, all trapped in this higher dimensional space. And these knots, you can't untie them smoothly.
You got it. It's like having a box full of knots that all look the same, but they're tied differently. You can't change one into another without cutting the rope.
That's mind-blowing. So theorem 1.9 is the key to understanding that.
Exactly. And it's not just about those codimension 0 submanifolds like the sphere. Yasui extends it to codimension 1 submanifolds, which are like 3 manifolds embedded in a 4 manifold.
So you're saying we can knot our entire three-dimensional space?
It's possible.
Inside a higher dimension?
Yeah. That's what theorem 1.11 explores. It gives us the tools to see how we can modify a 3 manifold embedded in a 4 manifold into infinitely many exotic versions.
Hold on. Need a minute to process all this. This is some next level complexity. It really shows how different dimension 4 is from our everyday world.
Right. In dimensions 1, 2, and 3, smooth and topological structures are basically the same.
Right.
But in dimension 4, they're not. And that's where all these exotic things start happening.
It's like dimension 4 is a secret door to a whole universe of possibilities.
Right.
But what does this tell us about smooth structures in general?
It tells us they're incredibly subtle and powerful. They can distinguish spaces that look identical topologically, revealing a whole hidden layer of complexity that we're just starting to understand.
Right. Okay. And what about genus functions? Are they involved in understanding these exotically knotted submanifolds?
Absolutely. They're still key to navigating this exotic world. Theorem 1.45 shows how genus functions behave when we do things like connected sums and boundary sums with certain four manifolds.
So even when we combine these exotic four manifolds with other spaces, the information in their genus functions is still important.
Yeah. The big idea here is stability. Under certain conditions, the differences in those genus functions, the algebraic differences, they stick around even after we do these operations. It's like the exotic nature of the original manifolds is built in, and it's hard to erase.
Wow, so we can build up more complex spaces?
Yeah.
But those fundamental differences in the smooth structure reflected in the genus functions,
Absolutely.
they're still super important for understanding the whole thing.
Exactly. And this has big implications for how we can classify and understand exotic four manifolds. Those differences aren't just superficial, they tell us something deep and fundamental about these spaces.
It's like we're putting a puzzle together, and the genus functions are giving us clues about the overall picture.
Yeah, exactly. But Yasui doesn't stop there. He goes on to talk about the role of S2 links in constructing these exotic structures.
Oh?
These S2 links are like collections of two-dimensional spheres all linked together in a four-sphere.
So we're talking about spheres, but linked together in 4 dimensions.
Right. And Lemma 8.1 shows that you can use these S2 links like building blocks to create all sorts of exotic four manifolds.
So you take these linked spheres, do some 4-dimensional surgery, and bam, you've got a new exotic four manifold.
You got it. And the variety you can create is amazing, from simple things like a surface times a disk to more complex stuff like Mazur-type contractible four manifolds.
So S2 links are like blueprints for exotic four manifolds.
Precisely. By choosing how you arrange the spheres and what surgeries you do, you can build a whole zoo of exotic spaces.
Wow. And does this construction affect genus functions?
Absolutely. Theorem 8.4 shows that genus functions stayed the same.
So they're preserved?
Yeah, preserved under connected sums and boundary sums with these submanifolds that you get from surgery on four manifolds.
So even when you combine these exotic four manifolds made from S2 links with other spaces, the information in their genus functions still hangs on.
It does. It's that stability, again, emphasizing how important genus functions are.
I see.
Yasui digs even deeper into this in theorems 8.7, 8.8, 8.9, and 8.10. He's looking at when those algebraic differences in genus functions are preserved, even after all these operations.
So it seems like the exotic nature of these manifolds is deeply ingrained.
It really is.
It resists change, even as we build more and more complex spaces from them.
That's right. But Yasui throws a curveball in theorem 9.9. It shows that even with genus functions, there are still mysteries in four-dimensional topology.
Oh, okay. What does it say?
It says there are infinitely many closed four manifolds that are not homeomorphic.
Wow.
But they have the same genus functions.
So there are exotic four manifolds that look identical if you just look at their genus functions, but deep down they're fundamentally different.
Exactly. It's a reminder that we still need to find new tools.
New invariants.
Yeah, new and better invariants to fully classify these exotic spaces and understand them completely.
So genus functions are powerful, but they don't tell us everything.
Right. There's still so much more to explore.
It's kind of humbling and exciting at the same time.
Yeah.
But before we get lost in the infinite possibilities, let's zoom out for a second. What are the bigger implications of Yasui's work? Like, why should we care about this?
That's a great question. On one hand, it's pure math at its best. It shows us that even in these abstract areas, there are amazing structures and unexpected things waiting to be found.
Like, we're explorers in a new world, and every step we take leads to new wonders and challenges.
Exactly. But it goes beyond pure math, too. Remember those connections to physics and space-time?
Oh, right. The idea that space-time itself could have these exotic structures.
Yasui's work gives us a way to look into those connections more deeply.
That could completely change how we understand the universe.
It really could. Imagine a universe where physics happens on a backdrop of exotic, smooth structures. It could lead to all kinds of new phenomena, maybe even help us understand dark matter and dark energy better.
It's incredible to think that these abstract math ideas could be so important for understanding the cosmos. But I have a feeling we're just getting started. There's so much more to discover.
Absolutely. Yasui's paper opens up so many possibilities. Researchers will be building on it for years to come. It's a great time to be working in four-manifold theory.
It sounds like it. But before we get too carried away, let's recap some of the key things we've learned from Yasui's work.
Okay, yeah.
What are the big takeaways?
I think the most important one is that dimension 4 is truly special. It's where smooth and topological structures can be completely different, leading to those exotic phenomena that are so counterintuitive.
And genus functions, even though they don't tell the whole story, they're still crucial for understanding this exotic landscape. They help us see the differences between smooth structures and how those differences behave when we combine manifolds.
Yeah. And maybe the most important takeaway of all, Yasui's work shows us that math is a living, breathing thing. It's always changing and pushing the limits of what we know. There are still mysteries out there and new discoveries to be made, even in these abstract areas like four-dimensional topology.
That's a great point. This has been an amazing dive.
It has.
But we're just getting started. So we're back, still diving deep into this world of exotic four manifolds with Yasui as our guide.
Yeah, and we've talked about how these exotic structures exist, right?
Oh.
That we can build them using those cool quarks.
Right. But things get even more interesting when we zoom in on submanifolds within those spaces.
Oh, absolutely. It's like we're going deeper into the rabbit hole and things get weirder and weirder. Yasui really focuses on knotted submanifolds.
Yeah. Knotted submanifolds. That's where things get really interesting.
Right. So picture this. You've got this familiar three-dimensional object, like, say, a sphere.
Okay, a sphere. I can picture that.
Now, imagine embedding that sphere in a four-manifold. Yasui shows that with these exotic, smooth structures, you can actually knot that sphere in ways that are impossible in our regular 3D world.
Wait, hold on. So you're saying we could have, like, infinite versions of a knotted sphere, all tucked away in this higher dimension, and they're all topologically the same, but these knots, you can't just untie them smoothly.
Exactly. It's like having a box full of knots that look identical, but when you take a closer look, they're tied in totally different ways.
Okay, that is mind-blowing. So is that where theorem 1.9 comes in? The one about creating all these exotically knotted versions?
Precisely. And you can do this with more than just those codimension 0 submanifolds like the sphere. Yasui also extends the idea to codimension 1, which are like 3 manifolds embedded in a 4-manifold.
Whoa, hold on. So we're not just knotting spheres, we're talking about knotting our whole 3D space inside a higher dimension.
That's right. And Theorem 1.11 actually gives us the tools to explore that. It tells us we can modify a 3-manifold embedded in a 4-manifold into infinitely many exotic versions, each of them homology cobordant to the original.
Okay, I need a moment to wrap my head around that. That's like a whole new level of complexity. It just shows how different Dimension 4 is from the 3D world we're used to.
Absolutely. In Dimensions 1, 2, and 3, smooth and topological structures are basically the same. But Dimension 4 is like a whole other game. That's where all these exotic things start popping up.
It's like we've opened a door to a whole new universe of possibilities. But what does this all mean for how we understand smooth structures?
Well, it shows us just how subtle and powerful they really are. They can distinguish between spaces that look the same topologically, like those knotted spheres. It's a whole hidden layer of complexity that we're just starting to figure out.
Okay, that makes sense. And what about genus functions? Do they help us understand these knotted submanifolds too?
Oh, absolutely. They're still essential tools for navigating this exotic world. Yasui shows in Theorem 1.15 how genus functions behave when we start combining 4-manifolds with things like connected sums and boundary sums.
Right, so even when we take those exotic 4-manifolds and combine them with other spaces, the genus functions are still important.
Precisely. It all comes down to stability. Under certain conditions, those differences in the genus functions, the algebraic differences, they stick around even after we do these operations.
Okay, so it's like the exoticness is built in and it's not easy to get rid of.
Exactly. And that has big implications for how we classify and understand these exotic 4-manifolds. It tells us those differences aren't just superficial, they're deeply rooted in the structure of the spaces.
Wow, so even as we create more and more complex spaces, those differences in the smooth structure, the ones reflected in the genus functions, they're still key to understanding the bigger picture.
Absolutely. And then Yasui takes things even further by bringing in S2 links.
Okay, S2 links. Remind me, what are those again?
They're like these collections of two-dimensional spheres all linked together within a four-sphere.
So we're talking spheres, but linked together in 4 dimensions.
Exactly. And in Lemma 8.1, he shows how we can use these S2 links as building blocks to create even more exotic four-manifolds.
Okay, I'm trying to picture this. So we take those linked spheres, do some 4-dimensional surgery on them, and out pops a new exotic 4-manifold.
You got it. And the variety you can create is amazing. We're talking everything from simple things like a surface times a disk to more complex objects like those Mazur-type contractible 4-manifolds.
So the S2 links are like blueprints for exotic 4-manifolds.
Exactly. By choosing how those spheres are linked and what kind of surgery we do, we can build a whole zoo of exotic spaces.
That's wild. And what about the genus functions? Do they change when we do this construction?
Nope, they're preserved. Theorem 8.4 shows that genus functions are preserved under connected sums and boundary sums with these submanifolds we get from doing surgery on 4-manifolds.
Okay, so even when we combine those exotic 4-manifolds made from S2 links with other spaces, the genus functions don't change.
That's right. More evidence for that stability we keep seeing and how important genus functions are in understanding all of this.
I see. So it seems like the exoticness of these manifolds is really deeply embedded.
Oh, it definitely is. But, Yasui throws a curveball at us in Theorem 9.9. It shows that even with something as powerful as the genus function, there are still mysteries left to solve in 4-dimensional topology.
Oh, what does the theorem say?
It says there are infinitely many closed 4-manifolds that are not homeomorphic, but they all have the same genus functions.
Whoa, wait, so there are exotic 4-manifolds that look identical based on their genus functions, but deep down they're actually different.
Exactly. It's like they're wearing a disguise. It shows us that we still need new tools, better tools, to really see through those disguises and fully classify these exotic spaces.
So genus functions are awesome, but they don't tell us everything.
Right. There's still a whole world of exotic 4-manifolds out there waiting to be explored.
Well, here we are, wrapping up our deep dive into the world of exotic 4-manifolds. And wow, what a journey.
It really has been. We've gone from the basics of smooth structures and 4-manifolds all the way to these mind-boggling ideas of Corks and exotic knotting.
And Yasui's paper has been like our roadmap through this uncharted territory.
Absolutely. He lays out the existence of these exotic structures, shows us how to build them with Corks and cobordisms, and then dives into the implications for submanifolds, especially those knotted ones.
And we saw how those genus functions, while they're powerful tools, don't give us the whole picture.
Right. There's still so much more to learn, so much more depth to explore. Yasui's work is just the tip of the iceberg.
One of the things that really struck me was the whole idea that dimension 4 is something special. Like it's this weird space where smooth and topological structures can be so different, leading to all these exotic things that we just can't even picture in our 3D world.
It really challenges our intuition, doesn't it? We tend to think of dimensions as just adding another coordinate axis. But Yasui shows us that each dimension can have its own unique quirks, its own set of rules.
It makes you wonder what other strange things are happening in higher dimensions, things we can't even begin to imagine.
That's the beauty of math, though. It lets us explore these realms that are beyond our direct experience to push the boundaries of what we think is possible.
And who knows, maybe someday our understanding of those higher dimensions will unlock new secrets about the universe, just like Yasui's work has done for 4-manifolds.
It's an exciting thought for sure. But for now, let's stay grounded in the world of 4-manifolds. Before we finish up, I wanted to touch on that connection between exotic smooth structures and the structure of space-time itself.
Yeah, that was definitely one of those mind-blowing parts of Yasui's paper. The idea that space-time, the very fabric of our universe, could have these exotic, smooth structures is both fascinating and kind of unsettling.
It challenges our most basic assumptions about reality, right? If space-time can be smooth in different ways, what does that mean for the laws of physics, for causality, for the possibility of other universes with different smooth structures?
It's like we thought we were standing on solid ground, and now we're realizing it might be a lot more fluid and complex than we imagined.
Exactly. It opens up a whole Pandora's box of possibilities, both exciting and potentially scary. But it also highlights how deeply connected math and physics are, how these abstract mathematical ideas can have huge implications for our understanding of the universe.
It's a good reminder that the search for knowledge never really ends. There are always new mysteries to solve, even in areas that seem abstract like 4-dimensional topology.
You said it. And Yasui's paper is a testament to the power of human curiosity and the beauty of mathematical exploration. It shows us that even in the most abstract realms, there are profound connections to the real world and the fundamental nature of reality itself.
So as we wrap up this deep dive, what's the one big takeaway you'd like our listeners to walk away with?
I think the biggest thing is that Dimension 4 is truly unique. It's a place where our intuition from lower dimensions breaks down, and all these unexpected, exotic phenomena appear. It's a world of quarks, knotted submanifolds, and genus functions that reveal a hidden depth and complexity we're just beginning to grasp.
And maybe even more importantly, it's a reminder that math is a living, breathing field, constantly pushing the boundaries of knowledge and opening up new paths for exploration.
Absolutely. There's so much more to discover, and Yasui's work has given us a roadmap for future adventures. It's a thrilling time to be working in four-manifold theory, and I can't wait to see what new wonders we uncover next.
Well, I think it's safe to say our brains are officially full after this deep dive, but in a good way. We've caught a glimpse of a world that's both strange and beautiful, a world where the usual rules of space and dimension don't quite apply, and all sorts of new possibilities open up.
And who knows, maybe one day we'll even be able to visualize these exotic four-manifolds and really appreciate their full beauty and complexity. But until then, we have the power of math to guide us.
Thanks for joining us on this incredible journey into the world of exotic four-manifolds. We hope you enjoyed the dive. Welcome back, everybody, for another deep dive. This time we're diving into exotic, smooth structures on four manifolds and their genus functions.
All right.
I've always found four manifolds fascinating.
Yeah.
They have this ability to hold these kind of hidden exotic structures, spaces that look the same topologically,
Right.
but are fundamentally different when you zoom in on their smooth structure. It's like having two seemingly identical sculptures.
Okay.
One carved from smooth marble and the other from rough granite.
Yeah.
To the casual observer, they might look the same.
Yeah.
But run your hand over them and you immediately feel the difference.
Right.
And that's the kind of subtlety that we're dealing with here.
Yeah, and what's even more exciting is the role of genus functions in this exploration.
Right.
Think of it as a way to measure the complexity of drawing two-dimensional shapes inside these four-dimensional spaces.
Okay.
Just like it's easier to draw a circle on a sphere than on a donut.
Right.
The genus function gives us a way to probe these exotic structures and see how twisted they are.
So it's like a mathematical tool that lets us feel the texture of these exotic four manifolds.
Exactly.
Even though we can't actually touch them.
Exactly. Yeah, and what's amazing is we're still just scratching the surface of this field.
Right.
Mathematicians have found tons of exotic four manifolds already, but the big questions are, how common are they?
Right.
And how much can genus functions tell us about them?
Right.
That's where the paper we're diving into today.
Okay.
Corks, Exotic Four Manifolds in Genus Functions by KOUICHI YASUI comes in.
All right.
And we've also got some supporting material on quark theory, exotic knotting, and smooth structures to help us along the way.
Okay. I'm ready to unpack this.
Yeah.
And from the looks of it, the first stop on our journey is to understand these quarks.
Yeah.
I remember reading about them before, but a little refresher would be great.
Sure.
They're special types of four manifolds, right?
They are. Imagine a quark with a subtle twist built into it.
Okay.
You can plug it into a four manifold with boundary.
Okay.
And while the overall shape might look the same, that twist introduces a fundamental change in the smooth structure.
Ah, okay. Now I remember. It's like trying to fit a square peg in a round hole, but with an extra dimension of weirdness. No matter how you try, it just won't fit smoothly.
Right.
Even though it might look like it should.
Exactly. And what's incredible is that this paper shows you can use these quarks to create not just one, but an infinite number of exotic versions of almost any four manifold with boundary. And get this. All these versions can have the same genus function.
Wait, really?
Yeah.
That's mind-blowing.
Yeah.
So you're saying we can have infinitely four manifolds that look the same topologically, even when we probe them with the genus function.
Right.
But they're all smoothly distinct.
They are.
Yeah, that challenges my intuition about how these things should work.
It really does.
Yeah.
And it highlights just how subtle and complex these smooth structures can be.
Yeah.
You can have these wildly different underlying geometries, but they all feel the same when you try to draw shapes inside them.
Okay. I'm going to need a moment to wrap my head around that.
Yeah.
It's like discovering that there are infinitely many ways to tie a knot that look identical, but require completely different manipulations to undo.
That's a great analogy. And this finding actually challenges a conjecture put forth by Lawson back in 1997.
Right, Lawson's conjecture.
Yes.
It stated that genus functions could be the key to completely distinguishing smooth structures on simply connected four manifolds. But you're saying this paper shows it's not always the case.
Unfortunately, no. It turns out Lawson's conjecture was a bit too optimistic. We know it's not true in general because of some clever counterexamples. However, those counterexamples had relatively simple second homology groups. This paper goes further and shows that even for four manifolds with more complex second homology groups, you can still have exotic structures with the same genus function.
So while genus functions are powerful tools, they don't tell the whole story. There's this hidden world of smooth structures that they sometimes miss.
Precisely. But the paper doesn't just focus on where genus functions fail. It also explores cases where they do work. For example, it highlights how for certain nice four manifolds, like rational and ruled surfaces, the genus function can distinguish smooth structures, especially within the realm of symplectic four manifolds.
So genus functions are a bit like a flashlight in a dark cave.
Great way to put it.
They illuminate some areas beautifully. But there are still shadows where exotic structures can hide.
A great way to put it, and one of the key findings of the paper is that even for a fixed four manifold, you can find infinitely many exotic versions with both equivalent and inequivalent genus functions. This means that sometimes those smooth structures are hiding in plain sight. And sometimes they cast distinct shadows even within the same four manifold.
Wow, that's a lot to process.
Yeah.
It's like having two sets of blueprints for the same building, but one set leads to a smooth, polished finish. While the other results in a rough, textured surface.
You got it. And the implications of this are quite profound. It means that the world of four manifolds is even richer and stranger than we initially thought.
So where do we go from here?
Well,
we've got these exotic structures popping up everywhere, but we're only beginning to understand how to detect them and what they mean.
Well, the paper goes on to explore several other fascinating avenues. One of them is the idea of exotically knotted submanifolds. Think of it like tying two knots that look the same from the outside. But no matter how you wiggle the rope, you can't transform one into the other without cutting and retying.
Wait, so it's like there's a hidden complexity?
Precisely.
In how these submanifolds are embedded within the four manifold. Even if they look the same from the outside.
Precisely. And what's really mind-bending is that this research shows you can take almost any submanifold of a four manifold and modify it to create infinitely many exotically knotted versions.
This is getting deep. We've got exotic structures built from quarks, exotic knotting. My head is spinning. But I have a feeling we're just getting started.
You are right.
What else did Yasui uncover in this paper?
Well, next we're going to explore how mathematicians combine four manifolds using something called connected sums and boundary sums. Think of it like gluing these spaces together along specific shapes and then seeing how their genus functions change.
So it's like playing with building blocks. But in higher dimensions.
Exactly.
We're going to see how sticking different four manifolds together affects how easily we can draw shapes inside the combined object.
Exactly. And what's really neat is that the paper shows how under certain conditions, gluing on these special building blocks can preserve or even change the differences in genus functions. This gives us a way to create even more families of exotic four manifolds with interesting properties.
This is incredible. So we can use these building blocks to amplify the exoticness, so to speak.
In a way, yes. And it turns out there's a certain type of exotic structure that's incredibly resilient to these gluing operations. The paper introduces the concept of stable exotic structures.
Stable.
Yes.
So no matter what, you glue on to these exotic four manifolds.
Right.
They stay exotic.
It means you can create exotic four manifolds.
Wow.
That stay exotic even after you glue on any Stein manifold that fits.
Okay.
Stein manifolds are a nice type of four manifold that often simplifies things.
Right.
So to see exotic structures persist, even when combined with them, is significant.
Wow. So it's like these exotic structures are deeply ingrained in the fabric of these four manifolds. They're not just surface level quirks.
Exactly. And it raises a really important question.
Okay.
Are there any limits to the prevalence of these exotic structures?
That's a good question. So far, it seems like exotic structures are surprisingly common in four manifolds with boundaries.
Right.
But what about closed four manifolds?
That's the million-dollar question.
Right.
The research we've discussed so far primarily focuses on four manifolds with boundaries. Whether this abundance of exotic structures holds true for closed four manifolds. Those without boundaries is a mystery waiting to be solved.
It's like we've explored the coastline of a new continent.
Right.
And found it teeming with exotic life.
Yeah.
But the vast interior remains uncharted.
Absolutely.
It makes you wonder what other surprises are hidden.
It does.
In the world of four manifolds.
Absolutely. And that's what makes this field so exciting.
Right.
There's so much we still don't know.
Yeah.
And each new discovery opens up even more questions.
This is truly mind-boggling.
Yeah.
We've covered so much ground.
Right.
But I feel like we've only just dipped our toes into the vast ocean of exotic four manifold theory.
You're right. And we still have a lot more to explore in the next part of this deep dive.
Okay.
We'll take a closer look at the mathematical machinery behind these amazing results, including some of the key proofs in Yasui's paper.
Okay. Get ready to delve into the fascinating world of homology theory, cobordisms, and the subtle dance between topology and smooth structures.
I can't wait. This is the kind of deep dive I live for.
Yeah.
The kind that pushes the boundaries of what we know.
Yeah.
And leaves us with more questions than answers.
Then buckle up. We're about to embark on the most thrilling part of our journey.
Welcome back to our deep dive into exotic four manifolds. Last time we explored the surprising abundance of these strange creatures and how they challenge our intuition about what it means for two spaces to be the same.
Exactly.
We also touched on how mathematicians use tools like GENUS functions and Corks to probe their hidden depths.
Yes.
And now it's time to roll up our sleeves and delve into the nitty-gritty math behind these mind-bending concepts.
Exactly.
Specifically, we're going to unpack some of the key proofs from the Yasui paper.
On Corks, exotic four manifolds, and GENUS functions.
Yes.
I'm ready to get my hands dirty. Where do we begin?
Well, one of the most crucial results in the paper is theorem 3.6.
All right.
It's all about constructing exotic four manifolds from generalized quarks.
Hold on, before we dive into the theorem itself.
Sure.
Can you remind me what a generalized quark is again?
Of course. Remember how we talked about quarks as these special four manifolds with a twist?
Right.
Well, a generalized quark is a kind of souped up version of that.
Okay.
It's a four manifold with a special self-homeomorphism on its boundary.
Okay.
That can't be smoothly extended to the entire four manifold. This non-extendable twist is what makes it so powerful for creating exotic structures.
Okay, so it's like a quark with an extra layer of complexity.
Okay.
Got it. Now, what does theorem 3.6 tell us?
It provides a recipe for creating exotic four manifolds by carefully gluing these generalized quarks to other four manifolds. The theorem states that if you have two four manifolds, let's call them X arrows and X arrow, that share the same boundary denoted by M.
Right.
And if there's a specific kind of mismatch between how their boundaries are glued to a certain invertible homology cobordism denoted by P, then the resulting four manifolds X zeros and X arrow P are guaranteed to be exotic, meaning they're not diffeomorphic to each other.
Whoa, that's a mouthful.
Yeah.
Let me see if I can break that down.
Sure.
We start with two four manifolds that share a boundary.
Right.
Then we introduce this thing called an invertible homology cobordism, which acts like a bridge between their common boundary and another three manifold.
Exactly. And the invertible part means we can attach this bridge and then detach it without changing the topology of the original four manifolds.
Okay, so it's like a temporary connection.
Right.
But what's this mismatch in the gluing that you mentioned?
Right. The theorem specifies that the gluing maps F and Fs must be chosen so that their compositions with a certain map from the fundamental group of the boundary M to the fundamental group of the cobordism P are different. This creates a kind of topological tension at the boundary, preventing the two resulting four manifolds from being smoothly equivalent.
So it's like trying to sew two pieces of fabric together.
Right.
But using different types of stitches along the seam.
That's a great analogy.
Even though the overall shape might look the same, the seam itself reveals that they were constructed differently.
That's a great analogy. And the proof of this theorem is quite clever. It involves taking the upside-down cobordism of P, denoted by Q, and gluing it to both XUSP and XUP to create new four manifolds. If those new four manifolds were diffeomorphic, it would imply that the original gluing maps, S and Fs, could be smoothly adjusted to match, which contradicts the initial conditions of the theorem.
So it's a proof by contradiction.
It is.
Showing that the exotic nature of the generalized Corks persists.
Yes.
Even after we attach this cobordism and then detach its inverse. I'm starting to see how this construction can generate all sorts of exotic four-manifold.
Exactly. And this actually builds on earlier work by Achbelut and Ruberman, who used a similar construction to create exotic pairs of four manifolds. But what's particularly exciting about Yasui's result is that it shows all four manifolds created by twisting a given generalized Cork in this manner are pairwise exotic.
Wow.
He leverages a specific cobordism P corresponding to a particular knot J to ensure that the original and modified four manifolds are homotopy equivalent, which is a crucial ingredient in the proof.
Wow, so we're using knot theory to generate exotic structures.
They absolutely are.
Knots really do seem to be the key to unlocking many of the mysteries of four manifolds.
They are now. One thing to note is that while the paper states the homotopy equivalence holds for any cobordism P with specific properties, the proof itself is only explicitly shown for the case where the original four manifold is incontractable.
Ah, so there's a potential gap there.
Yes.
A place where further investigation might be needed.
Indeed, but don't worry. Even if the original four manifold isn't contractible, the homotopy equivalence still holds in many cases. For example, if the original four manifold is simply connected, we can use Whitehead's theorem to establish the equivalence for more general cases. The paper includes a separate lemma 3.8, which establishes that for the specific cobordism used, the boundary component M is a deformation retract of P. This means that P can essentially be shrunk down to M without changing its essential topological properties.
So there's some extra work involved. If we're dealing with non-simply connected four manifolds. But the main idea of the proof still holds.
It does.
We can use this cobordism construction to generate a whole bunch of exotic four manifolds.
Precisely. And as the paper points out, for any generalized Cork of infinite order, meaning its twisting homeomorphism can be applied infinitely many times without ever becoming smoothly extendable. This construction gives us a way to generate infinitely many pairwise exotic four manifolds.
It's like having a mathematical machine that churns out exotic four manifolds on demand.
Exactly.
It makes you wonder if there's any limit of the variety of these exotic structures.
That's a fascinating question, and one that mathematicians are still grappling with. But before we get ahead of ourselves, let's shift gears a bit and explore another important aspect of this research, the relationship between four manifolds and their genus functions.
We talked about how genus functions can sometimes distinguish smooth structures, but not always. There's this delicate interplay between the two that I'm still trying to fully grasp.
It's a subtle relationship for sure. And one of the key results in the paper that sheds light on this is theorem 7.1. States that attaching a quasi-invertible cobordism to a four manifold preserves the genus functions.
Hold on. I'm going to need a quick refresher on what a quasi-invertible cobordism is. It's not quite the same as an invertible cobordism, right?
Yeah, it's a bit more nuanced.
Okay.
A quasi-invertible cobordism is almost like an invertible one, but with a slight twist.
Okay.
Imagine it like a path between 2 points where you can retrace your steps, but maybe not perfectly.
Yeah.
You might need to take a few detours along the way,
Okay.
but you'll end up back where you started. These detours, in the context of cobordism, involve performing surgeries on embedded circles.
Okay, so it's not a perfect inverse,
Right.
but close enough that it doesn't mess up the genus functions.
Right.
That's pretty remarkable.
Yeah.
How does the paper prove this theorem?
The proof is quite intricate.
Okay.
And involves a clever combination of homology theory and the properties of quasi-invertible cobordisms.
Okay.
It starts by attaching a quasi-inverse cobordism Q
Right.
to the modified four-manifold X to create a new four-manifold X's.
Okay.
Then by carefully performing surgeries on embedded circles within X, we obtain a four-manifold that's diffeomorphic to the original four-manifold X with a product cobordism attached.
So it's like we're performing a series of topological surgeries.
Exactly.
It's carefully reshaping the four-manifold without changing its fundamental properties.
Exactly. And by analyzing the homology groups of these modified four-manifolds and using the fact that the genus function is preserved under diffeomorphisms, we can conclude that the genus functions of X and X must be the same.
It's like solving a complex jigsaw puzzle. Rearranging the pieces and adding some new ones.
Yeah.
But ultimately preserving the overall picture.
Exactly.
Which in this case is the genus function.
A perfect analogy.
Okay.
And this theorem has some interesting consequences.
Okay.
For instance, if the inclusion map from the original four-manifold X into the modified four-manifold X induces an isomorphism between their second homology groups, then the genus function of X is algebraically equivalent to that of X. This tells us that in these cases, attaching a quasi-invertible cobordism doesn't change the essential information captured by the genus function, even if it creates a different smooth structure.
So in a way, these exotic structures are hiding in plain sight. They might be different smoothly.
Yes.
But from the perspective of the genus function, they look identical.
Precisely. And this leads us to another important concept explored in the paper. Stability under connected sums and boundary sums.
Yes. Remember how we were talking about gluing four manifolds together?
Yes.
How does that tie into the story?
Well, it turns out that under certain conditions, if we glue two four manifolds together using connected sums or boundary sums, and if their genus functions were different to begin with, they will remain different even after the gluing. This is a powerful result because it tells us that these differences in genus functions are robust and can persist even when we combine four manifolds in these specific ways.
So it's like the genus function is leading behind a fingerprint.
That's a great way to put it.
A unique signature that can't be erased.
Yes.
Even by these gluing operations.
That's a great way to put it. And this stability property has important consequences for classifying exotic four manifolds and understanding their subtle distinctions. It also hints at deep connections to other areas of mathematics, like knot theory and symplectic geometry.
This is incredible. We've gone from Corks and knot surgery to homology theory and algebraic equivalences. It's like we're weaving together different threads of mathematics to create a tapestry of exotic four-manifold theory.
That's a beautiful way to describe it.
Yeah.
And we're only just beginning to explore the richness and complexity of this tapestry.
I'm eager to see what other patterns and connections we'll uncover.
Right?
But for now, I think we need a moment to pause. And let all this information sink in.
That's a good idea. We've covered a lot of ground today.
Yeah, we have.
But we've only just scratched the surface of this fascinating world. In the next part of our deep dive, we'll continue to explore the implications of Yasui's research, including some truly mind-bending results related to exotically knotted submanifolds and the elusive question of whether this abundance of exotic structures extends to closed four manifolds. I can't wait. It seems like every step we take into this exotic landscape reveals even more mysteries and wonders.
I'm already looking forward to the next part of our adventure. Welcome back to the final part of our deep dive into the fascinating world of exotic four manifolds. I'm still trying to wrap my head around all the incredible concepts we've covered so far.
It is pretty wild, isn't it?
It's amazing to think that these seemingly simple four-dimensional spaces can harbor such complex and hidden structures.
Yeah, and remember those exotic four manifolds with equivalent genus functions we talked about?
Yeah.
The ones that are like identical twins leading secret lives? Well, now we're going to delve deeper into how those twins are created, mathematically speaking.
I'm all ears. We've talked about how they exist.
Right.
But now I want to know the nuts and bolts of how mathematicians actually construct them.
That's where Theorem 9.4 comes in.
Right.
It provides a sort of recipe for generating these exotic families.
Okay.
It starts with a set of generalized quarks that are pairwise inequivalent, meaning they're all smoothly distinct.
Okay.
But here's the catch. Their twisting homeomorphisms can be extended to self-homeomorphisms that preserve the genus function.
Okay.
Then, by carefully applying a combination of quark twists and attachments of invertible cobordisms, we can create a whole family of exotic four manifolds that are all topologically the same but smoothly distinct, and whose genus functions are all equivalent.
So it's a delicate dance of cutting, twisting, and gluing.
Right.
But somehow, through all that manipulation, the genus function stays the same. It sounds almost magical.
It is quite remarkable. And the proof of this theorem beautifully combines the properties of generalized quarks, invertible cobordisms, and the fact that genus functions are preserved under certain types of homeomorphisms.
Right.
It's a testament to the power of abstract mathematical tools to create and understand these incredibly complex objects.
It's like we're using the very fabric of topology and smooth structures to weave these exotic families, all sharing the same fingerprint, their genus function.
Exactly.
It's a mathematical magic trick.
A very apt description. And the beauty of this theorem is its versatility. We can apply it to a wide variety of generalized quarks, allowing us to generate a rich tapestry of exotic four manifolds. For instance, the paper uses this construction to prove Theorem 9.5, which shows that any four-dimensional two-handle body, a specific type of four manifold built from handles, can be modified to admit infinitely many exotic smooth structure.
All with equivalent genus functions.
Hold on, let me make sure I'm following. You're saying that no matter what two-handle body you start with,
exactly,
you can always find an infinite number of exotic versions.
You got it.
That feel the same to the genus function. Even though they're fundamentally different in their smooth structures.
Precisely.
That's truly mind-boggling.
It is, and this result significantly extends earlier work by KOUICHI and Yasui, which showed that you could create arbitrarily many exotic smooth structures on two handle bodies, but only for those with non-zero second Betti numbers.
So this research is pushing the boundaries of what we know about the prevalence of exotic smooth structures. Especially in the context of two-handle bodies.
Exactly.
And it's all thanks to these clever constructions involving quarks and invertible cobordisms.
Exactly. Now, let's rewind a bit. And recall Lawson's conjecture. Remember, it had proposed that genus functions could completely distinguish smooth structures?
For certain types of four manifolds. While this conjecture turned out to be false in general, this paper explores cases where it does hold. Specifically for certain nice four manifolds. Like rational and ruled surfaces. Within the realm of symplectic four manifolds.
Yes, symplectic geometry. That means we're stepping into a world where these four manifolds have an additional geometric structure. A kind of underlying symmetry. That goes beyond just their topology and smooth structure.
Symplectic four manifolds possess a special two-form that provides a rich geometric structure and allows us to use powerful tools from symplectic geometry to study their properties. And in these cases, as shown in Proposition 2.6, the genus function is indeed powerful enough to completely determine the smooth structure.
So for these special symplectic four manifolds, the genus function acts like a perfect fingerprint. Uniquely identifying each smooth structure. But when we step outside the realm of symplectic geometry, things get a lot more complicated, right?
Absolutely. The paper highlights this complexity beautifully with theorem 9.7. A truly mind-bending result. Shows that there exist infinitely many pairwise exotic, simply connected four manifolds with algebraically inequivalent genus functions. But here's the twist. Each of those genus functions is also equivalent to infinitely many other pairwise exotic four manifolds.
Wait, let me see if I understand this correctly.
Okay.
We have these infinite families of exotic four manifold. And their genus functions can distinguish some of them, but not others. It's like trying to sort out a room full of identical twins. Where some have subtle differences, but others are completely indistinguishable.
It highlights the incredible intricacy of the relationship between smooth structures and genus functions. Theorem 9.7 tells us that genus functions alone aren't enough to fully unravel the mysteries of exotic four manifolds. We need a whole toolkit of mathematical instruments. And that's where tools like Seiberg-Witten invariance and Heegard-Flower homology come in. They provide different perspectives and can sometimes distinguish smooth structures when genus functions fall short.
So it's like we need a whole orchestra
Exactly.
of mathematical techniques to appreciate the full symphony of exotic four-manifold theory.
Precisely. And the search for new tools and techniques is an ongoing and exciting area of research. For example, the paper touches on the idea of exotically knotted submanifolds, but it leaves a lot of open questions. Could these exotic knottings provide even more sensitive probes for distinguishing smooth structures? We don't know yet, but it's a tantalizing possibility.
It seems like the more we learn about exotic four manifolds, the more we realize how much we don't know.
That's the beauty of mathematics. It's a never-ending journey of discovery. And this particular journey is far from over. One of the biggest unanswered questions in the field is whether this abundance of exotic structures extends to closed four manifolds, those without boundaries. It's like we've mapped out the coastlines of these exotic continents, but the vast interiors remain largely unexplored. What wonders and mysteries await us there?
It's an incredible thought. A whole universe of exotic structures. Potentially hidden within these closed four manifolds. Who knows what we might find if we can develop the tools to explore them.
Well, that's the challenge, isn't it? To boldly venture into the unknown and see what we can discover. And with brilliant mathematicians like KOUICHI YASUI paving the way, I have no doubt that we're on the cusp of even more remarkable discoveries in the world of exotic four manifolds.
I can't wait to see what the future holds for this fascinating field.
Me too.
And a huge thank you to our listener for sending us this amazing stack of sources.
Yes, thank you.
This has been a truly mind-expanding deep dive.
It has.
That's a wrap on this deep dive. Until next time, keep those minds curious.
Yes.
And we'll see you on our next adventure into the fascinating world of mathematics. Welcome to another deep dive. Today, we're going to be looking at exotic smooth structures on four manifolds.
Oh, very cool.
Yeah. And to guide our exploration, we're going to be taking a look at a paper by KOUICHI YASUI called Corks, Exotic Four Manifolds and Genus Functions.
Excellent choice.
So before we jump into the specifics of the paper, though, can we kind of take a step back and define what we mean when we say four manifold?
Sure, yeah. A four manifold is a space that requires four coordinates to describe.
So it's like a higher dimensional version of a sphere or a donut.
Precisely.
Okay, and then what gets really interesting is that that's where the idea of exotic smooth structures comes into play.
Yeah.
So what do we mean by that?
So two four manifolds can be topologically the same, but not smoothly the same.
So it's like you can't smoothly map one onto the other without cutting or tearing.
Right.
Okay, that's pretty wild.
Right.
And you're saying that doesn't happen in lower dimensions?
It doesn't happen in dimensions 1, 2, or 3. If they're topologically the same, they're also smoothly the same.
Okay, so dimension 4 is where things get kind of crazy.
Yeah.
And that's where this concept of the genus function comes in, right?
Right. The genus function can be used to detect those exotic smooth structures.
So can you explain a little bit about the genus function? What is that?
Sure. The genus function is a map from the second homology group of a four manifold to the integers.
Okay, and what is the second homology group?
So that measures the two-dimensional holes in the four manifold.
Okay, and how does the genus function then? How does it measure those?
It assigns to each homology class an integer, which is the minimal genus of a surface representing that homology class.
So are we looking at the simplest surface that we can find?
Yeah, exactly. The simplest possible surface that can represent that homology class.
Okay, and how do we know what that is?
Well, the genus of a surface is intuitively the number of holes it has.
Like a donut would have a genus of 1.
Yeah, a donut has a genus of 1, a sphere has a genus of 0.
Gotcha. Okay, so then we have exotic smooth structures, and the genus function can tell us a little bit about those.
Right.
And you were mentioning that Yasui looks at cork twisting. What is cork twisting?
Right, so cork twisting is a way to construct exotic smooth structures.
Okay.
A cork is a contractible four-manifold.
What does contractible mean?
It means that you can shrink it down to a point.
Oh,
And so you can cut out this cork and glue it back in, but with a twist.
Yeah.
And that's the cork twist. And that will change the smooth structure without changing the topology of the four-manifold.
Okay, so can you give me like an analogy for that to help me visualize what's going on?
Well, one way to think about it is, like, imagine you have a sphere.
Yeah.
And you can tie a knot in that sphere.
Okay.
And the knot is sort of the cork.
Okay.
And the sphere is the larger four-manifold.
Gotcha.
And by twisting the knot, you're changing the smooth structure of the sphere, but topologically, it's still a sphere.
That makes sense. Okay. So we've got cork twisting, and that can give us these exotic smooth structures. And then you mentioned also generalized corks.
Right. So generalized corks are corks that are not necessarily contractible.
Okay, so we don't have to shrink them down to a point.
Right.
And why are we looking at generalized corks? What's the benefit of those?
It turns out that they can be used to create exotic smooth structures on a much broader class of four manifolds.
Okay, including two handle bodies.
Right.
And what's a two handle body?
A two-handle body is a four-manifold that's built by attaching one handles and two handles to a zero handle.
Okay, so we're like building up a four manifold from simpler pieces.
Exactly.
And then Yasui does some pretty amazing stuff with these generalized corks and cork twisting, right? Like he shows that a lot of four manifolds can have infinitely many exotic smooth structures with genus functions that are equivalent.
That's right. So you can have infinitely many exotic smooth structures, all of which have the same genus function.
Wait, so the genus function can't tell those exotic structures apart? That's pretty wild.
It is.
Okay, so what does that actually mean? What's the takeaway from that?
It means that the genus function is not a complete invariant for smooth structures on four manifolds.
So it can tell us some things, but it can't tell us everything.
Exactly.
Okay, so it seems like we're only beginning to scratch the surface of this really complex and fascinating world of four-dimensional topology.
Yeah.
Before we move on to the specifics of Yasui's results, though, I think it'd be helpful to take a closer look at some of the key mathematical ideas involved, starting with the definition of exotic smooth structures themselves.
Okay, yeah, that's a good idea.
So, formally, how do we define a smooth structure on a manifold?
A smooth structure on a manifold, it's a way to define what it means for a function on that manifold to be differentiable.
Okay.
And the way we do that is we equip the manifold with what we call a smooth atlas.
A smooth atlas?
Yeah.
What is that?
It's like a geographical atlas.
Right.
It's a collection of maps, each covering a portion of the manifold. And these maps can be stitched together smoothly.
Okay.
So you can move from one map to another without any jumps or discontinuities.
So we can move smoothly from one part of the manifold to another without any sudden changes.
Precisely. And a smooth atlas on a four-manifold is a collection of charts, which are homeomorphisms from open sets in the manifold to open sets in four-dimensional Euclidean space.
So each chart kind of tells us what a piece of the manifold looks like.
That's right.
Okay.
And then the transition maps between these charts need to be smooth.
So the way we go from one chart to another has to be smooth as well.
Exactly.
So it's like ensuring that all the pages in our atlas match up perfectly.
Right.
Okay, I think I'm following so far.
Okay, good.
So how do we then define what it means for two four manifolds to be exotic?
So two smooth four manifolds are considered exotic if they are homeomorphic but not diffeomorphic.
Okay, so homeomorphic means topologically the same, right?
Right. So there's a continuous map between them that has a continuous inverse.
Okay, so we can continuously deform one into the other.
That's right.
And then diffeomorphic, that means smoothly the same.
Right. So there's a smooth map between them that has a smooth inverse.
So exotic means we can deform them into each other, but we can't do it smoothly.
Precisely.
Okay, and you said earlier that this only happens in dimension 4 or higher.
That's right. In lower dimensions, homeomorphic manifolds are always diffeomorphic.
So what is it about dimension 4 that allows for this distinction?
Well, that's a deep question that mathematicians are still trying to understand.
Yeah.
It seems that dimension 4 is sort of a critical dimension where a lot of the tools and techniques that work in lower dimensions break down and new phenomena emerge.
Okay, so it's where things start to get really interesting.
Yeah.
And a little bit weird.
Right.
Okay, and we're focusing on exotic smooth structures, so are there different types of exotics that we might encounter?
There are two main types, small exotics and large exotics.
Okay, what are those?
So small exotics arise when you're dealing with non-compact four manifolds.
Okay, so those are manifolds that extend infinitely in some direction.
That's right.
Okay.
And small exotics are characterized by the exoticness being concentrated in a compact region.
So if we zoom out far enough, the exotic structures kind of blend together.
Precisely.
Okay, and then what was the other kind?
Large exotics. And those occur when you have closed four manifolds.
So those are manifolds that are like finite, self-contained.
Exactly.
Yeah.
And for large exotics, the exoticness pervades the entire manifold.
So there's no region where the structures become indistinguishable.
That's right.
Okay, I think I'm starting to get a handle on the different types of exotic phenomena we might see.
Good.
Now, to really dive into Yasui's work, I think we need to take a closer look at the genus function.
Yeah.
So how is that formally defined?
The genus function is a map that goes from the second homology group of the four manifold to the integers.
Okay, and remind me again, what's the second homology group?
The second homology group captures information about the two-dimensional holes in the manifold.
Okay.
It's a way to algebraically represent how two-dimensional surfaces can be enclosed in the four manifold.
So, like, if our four manifold was a block of Swiss cheese, the second homology group would tell us about the different types of holes in the cheese.
That's a great analogy, yeah.
And then the genus function, it takes each of those holes and assigns it a number.
Right, and that number is the minimal genus of a smoothly embedded surface that can represent that homology class.
So it's the simplest surface we can find to fill in that hole in the manifold.
Exactly.
Okay, and smoothly embedded, what does that mean?
It means that the surface sits nicely inside the four manifold.
Right.
No sharp corners, no self-intersections.
So it's like a smooth sheet lying in the four-dimensional space.
That's right.
Okay, and why do we need to require that the surface be smoothly embedded?
Because we want the genus function to be well-defined.
Oh.
We don't want it to depend on which surface we choose to represent the homology class.
So it's got to be a property of the homology class itself, not just the specific surface we happen to pick.
Precisely.
Okay, and how do we actually calculate this minimal genus? It seems like that could be pretty tricky.
It is tricky, yeah. It often involves using a lot of tools from algebraic topology and differential geometry.
Like what?
Things like intersection forms, Seiberg-Witten invariants, Heegaard-Floer homology.
Wow, that sounds pretty intense.
It is.
But the payoff is that we get this really powerful invariant that can tell us a lot about the smooth structure of a four-manifold.
Right.
Okay, now before we move on to Yasui's results, I'd like to touch on adjunction inequalities, because I think that's relevant here.
Yeah, those are definitely relevant.
So can you explain what those are and how they relate to the genus function?
Sure. So adjunction inequalities, they provide bounds on the genus of a surface based on its homology class and how it intersects with other surfaces.
So it's like a set of rules that tell us how simple a surface can be based on where it is and how it interacts with other things in the manifold.
Exactly. And these rules come from the connections between topology, geometry, and analysis that we see in dimension 4.
Right, because dimension 4 is where all the cool stuff happens.
Exactly.
Okay, so can you give me an example of an adjunction inequality?
Sure. The Thom conjecture is a famous example.
Okay.
It states that if you have a smooth surface in complex projective two-space,
Yeah.
the genus of that surface is greater than or equal to the genus of an algebraic curve representing the same homology class.
So it's like saying that algebraic curves are the most efficient way to fill in a homology class.
That's right.
Okay, and how do adjunction inequalities help us in the context of exotic, smooth structures?
Well, they provide these constraints on the genus of surfaces, and those constraints can tell us something about the smooth structure of the four-manifold.
Gotcha.
So, for instance, Yasui uses adjunction inequalities to show that certain Cork twists have to change the genus function.
So it's like the Cork twist forces us to make the genus function more complicated.
Precisely.
Okay, this is all starting to come together. Good. We've got smooth structures, we've got the genus function, and we've got these adjunction inequalities.
Right.
I think we're ready to start diving into the specifics of Yasui's paper.
Okay, let's do it.
So the paper begins by defining a bunch of important terms.
Yeah.
And one of those is a finite order quark.
Right.
So could you explain what that is?
The finite order quark is a quark where some power of the twisting diffeomorphism extends to a self-diffeomorphism of the entire quark.
Okay, so if we twist the quark enough times, we get back to where we started.
That's right.
Okay, and then we also have infinite order quarks.
Yeah, those are quarks where no finite power of the twisting diffeomorphism extends to a self-diffeomorphism.
So no matter how many times we twist, we never get back to the original smooth structure.
Right.
And those infinite order quarks, those are the really powerful ones for creating exotic structures, right?
That's right.
Because each twist potentially gives us a new exotic structure.
Exactly.
Okay, and then Yasui also defines a quark twist.
Yeah, that formalizes the process of twisting a quark.
Okay, so you remove the quark, twist it, and glue it back in.
Yeah, we talked about that before.
Right.
And then he also has generalized quark twists.
Right.
Which I assume those are quark twists, but with generalized quarks.
Exactly.
Okay.
And as we talked about, generalized quarks allow you to create exotic structures on a wider class of four manifolds.
Right. Okay, so we're setting ourselves up to be able to explore these exotic structures on a whole bunch of different manifolds.
Precisely.
Okay. And one of the first big results in the paper is this theorem, theorem 1.2, which says that every four-dimensional two-handle body can be modified to have infinitely many exotic smooth structures with equivalent genus functions.
Right.
So we can have infinitely many different exotic structures, but the genus function can't tell them apart.
That's right.
Okay, and remind me one more time, what's a two-handle body?
It's built by attaching one handles and two handles to a zero handle, which is just a four ball.
Okay, so it's like building up a four-manifold from these simpler pieces.
Right.
And then how does Yasui prove this theorem? What's the strategy? The proof relies on the existence of infinite order generalized quarks, performing generalized quark twists, and then using the properties of what are called quasi-invertible cobordisms.
Okay, we've talked about generalized quarks and quark twists, but what are quasi-invertible cobordisms?
A cobordism is a way to connect two manifolds.
Okay.
It's a higher dimensional manifold whose boundary is the disjoint union of the two manifolds that you want to connect.
So it's like a bridge between the two.
Exactly.
Okay.
And a quasi-invertible cobordism is a cobordism that has an inverse.
Okay.
Meaning if you glue it to its inverse, you get a cobordism, which is almost a product cobordism.
Okay. And why is this property of being almost a product cobordism important?
Because it allows you to control the genus function.
Okay.
When you attach a quasi-invertible cobordism to a four-manifold, the genus function doesn't change too much.
So it's like a buffer that protects the genus function from the changes caused by the quark twist.
That's right.
Okay, so in the proof, Yasui uses a generalized quark twist to create the exotic structures, and then he uses a quasi-invertible cobordism to make sure the genus function stays the same.
That's right.
That's pretty ingenious.
Yeah.
And that proves theorem 1.2, which is that any two-handle body can be modified to have infinitely many exotic structures with the same genus function.
Right.
Okay, but then he doesn't stop there, right? He extends this result to other types of four manifolds as well.
Right. In theorem 1.4, he shows that any four-manifold that embeds into a symplectic four-manifold with a weakly convex boundary.
Okay, now we're getting into some new terms here. Can you remind me what a symplectic four-manifold is?
Sure. It's a four-manifold equipped with a two-form, which is called a symplectic form.
Okay.
And that form gives the manifold a rich geometric structure.
So it's like we're adding another layer of structure on top of the smooth structure.
Exactly.
Okay, and what does weakly convex boundary mean?
It basically means that the boundary can be bent outwards in a certain way. And this condition is important because it allows us to extend the symplectic four-manifold to a closed symplectic four-manifold.
So we need that weakly convex boundary condition so that we can complete the symplectic picture.
That's right.
Okay, and then theorem 1.4 says that any four-manifold that can be embedded into one of these symplectic manifolds with a weakly convex boundary, those also have infinitely many exotic structures with equivalent genus functions.
Right.
Okay, so we've expanded our class of manifolds that exhibit this behavior.
Yeah, significantly.
So we've got two handle bodies, and now we've got these other four manifolds that can be embedded into symplectic manifolds.
All right.
Okay, this is really remarkable.
It is.
So we've seen how Yasui constructs these families of exotic four manifolds. But he also explores the limits of this phenomenon, right? Like he shows that there are infinitely many exotic four manifolds with inequivalent genus functions.
Right.
But each of those genus functions is equivalent to infinitely many other exotic four-manifolds.
That's right. That's theorem 1.6.
Okay, and that one is a little bit trickier to wrap my head around. Can you help me understand what's going on there?
So the idea is to leverage the families of exotic four-manifolds that we've already constructed.
Okay.
So we start with a collection of four manifolds that have different genus functions.
Yeah.
And we know that each of those manifolds gives rise to an infinite family of exotic structures with the same genus function.
Right, because we can keep doing Cork twists.
Precisely.
Okay.
So what we get is this kind of branching structure where each of the original manifolds is like a branch.
Yeah.
And each branch contains infinitely many exotic structures with the same genus function.
Okay.
But the different branches have different genus functions.
So it's like a family tree of exotic manifolds.
That's a good way to think about it.
Where each branch is a family with the same genus function, but different branches have different genus functions.
Precisely.
Wow, so it's like this incredibly complex web of relationships between exotic structures and genus functions. It's really blowing my mind.
It is, yeah. This is pretty wild stuff.
Okay, so we've seen that genus functions can distinguish some exotic structures, but not others.
Right.
What does that tell us about the relationship between smooth structures and topology in dimension 4?
It tells us that it's a very subtle and complex relationship.
Yeah.
We need more tools than just the genus function to fully understand it.
So it's like we're just getting started in our exploration of this world.
That's right.
Okay, well, before we move on to part 2, can we recap the key ideas we've covered so far?
Sure.
So we started with the definition of smooth structures and exotic manifolds.
Right.
And we talked about how this distinction between smooth and topological structures only arises in dimension 4 and higher.
Right.
And then we defined the genus function and discussed how it can be used to detect exotic smooth structures.
Yeah.
We also talked about adjunction inequalities and how they provide constraints on the genus of surfaces.
Right.
And then we got into Yasui's work with Corks, Cork twists, and generalized Cork twists. And we saw how he uses those to prove that a lot of different four manifolds can admit infinitely many exotic smooth structures with equivalent genus functions.
Exactly.
And we also saw how he demonstrates the complex relationship between exotic structures and genus functions by constructing those families of exotic four manifolds with inequivalent genus functions.
That's right.
Okay, this has been a really great overview, and I'm excited to keep exploring this topic in part 2.
Me too.
So we'll see you all then.
See you then.
Welcome back. Last time we laid the groundwork for understanding exotic smooth structures and their relationship with the genus function.
Yeah, we started to get into Cork twisting and quasi-invertible cobordism.
Right. So I'd like to dive a bit more into the specifics of Yasui's proofs.
Sure.
Where should we start?
Well, let's go back to theorem 1.2.
Okay.
That states that every four-dimensional two-handle body can be modified to have infinitely many exotic smooth structures, all with equivalent genus functions.
Okay, so that was the one where we have all those exotic structures, but the genus function can't tell them apart.
Precisely.
Okay, and the proof of that theorem uses infinite-order generalized Corks, generalized Cork twists, and quasi-invertible cobordisms.
Right.
Can we just break those concepts down one by one? I want to make sure I'm following all the pieces here.
Sure, yeah. Let's start with infinite-order generalized Corks.
Okay.
So as we discussed, a Cork is a four-manifold with a twisting self-diffeomorphism of its boundary.
Yeah, and a generalized Cork doesn't have to be contractible.
Right.
So we have more flexibility there.
Exactly.
Okay, and then infinite order means that no matter how many times we twist it, we don't get back to the original smooth structure.
Right.
Okay, so how do we even know that these infinite order generalized Corks exist? How do we find them?
Well, Yasui constructs them carefully.
Cool.
He takes a four-manifold that admits what's called a Stein structure.
Okay, what's a Stein structure?
Essentially, it gives the four-manifold a kind of complex scaffolding.
Right.
It allows us to view the manifold through the lens of complex geometry.
So it's like we're adding a complex structure on top of the smooth structure.
Right.
And he embeds this Stein manifold into a symplectic four-manifold.
Okay.
And this allows him to use a technique called knot surgery to create these distinct smooth structures.
Okay, knot surgery. Now that sounds interesting.
Yeah.
What is that?
So it's a technique where you take a four-manifold that contains a torus.
Okay.
And you cut out a neighborhood of that torus.
Okay.
And then you glue back a different four-manifold that's obtained by doing surgery along a knot in the 3-sphere.
So it's like we're using a knot to change the smooth structure of the 4-manifold.
Exactly.
Okay, that's pretty wild.
Yeah.
So he uses this knot surgery to create these infinite order generalized quarks.
Right.
And then he uses them to perform generalized quark twists on 2 handle bodies.
Precisely.
Okay.
And as we've discussed, a 2-handle body is built by attaching handles to a 4-ball.
Right.
So by twisting this infinite order quark, he can create infinitely many distinct exotic smooth structures on the 2-handle body. Okay, so each twist gives us a new exotic structure.
Right.
But the key to theorem 1.2 is that these structures all have equivalent genus functions.
Right.
So how does he make sure that happens?
That's where the quasi-invertible cobordisms come in.
Okay.
He constructs a specific quasi-invertible cobordism that connects the original 2-handle body to each of these exotic manifolds that he's created.
Okay, remind me again what's so special about quasi-invertible cobordisms.
So these cobordisms act as a bridge between the different smooth structures.
Okay.
But they have this property that they're almost product cobordisms. And that property ensures that when you attach the cobordism, the genus function doesn't change too much.
So it's like it protects the genus function from being affected by the quark twist.
Precisely.
Okay, so the quark twist creates the exotic structures, and the quasi-invertible cobordism makes sure the genus function stays the same.
Right.
Okay, that's really clever. And that proves theorem 1.2.
Right.
Okay, and then what about theorem 1.4? That one extends this result to other types of 4-manifolds, right?
Right. So theorem 1.4 says that any 4-manifold that embeds into a symplectic 4-manifold with a weakly convex boundary also admits infinitely many exotic structures with equivalent genus functions.
Okay.
So now we're not restricted to just 2 handle bodies.
Right, we're expanding our class of manifolds again.
Exactly.
Okay, so how does he prove theorem 1.4? Is it similar to the proof of theorem 1.2?
It follows a similar strategy, yeah.
Okay.
But we need some additional tools.
Okay.
First of all, we need to make sure that our 4-manifold can be embedded into a closed symplectic 4-manifold.
Okay, and that's where the weakly convex boundary condition comes in.
Exactly.
So we need that condition to make sure we can complete the symplectic picture.
Right.
Okay, and once we have a closed symplectic 4-manifold, then what?
We can use some techniques from symplectic geometry, like Gromov's H principle, to show that we can actually embed our 4-manifold into this closed symplectic 4-manifold.
So we're using the geometry of the symplectic manifold to our advantage.
That's right. And this embedding allows us to construct a specific infinite order generalized quark that contains our 4-manifold in a certain sense.
So it's like we're building a custom quark for our manifold.
Precisely.
Okay, and then what?
Then we can perform a generalized quark twist along this quark, just like in theorem 1.2, to create infinitely many exotic structures.
Okay.
And again, we use a quasi-invertible cobordism to ensure that the genus function remains the same.
So the general idea is similar to the proof of theorem 1.2.
Right.
But we need to do some extra work to handle this more general class of manifolds.
Exactly.
Okay, this is really impressive. So we've got these 2 theorems showing us that lots of 4-manifolds can have infinitely many exotic structures with the same genus function.
Yeah.
But Yasui takes it even further, right? He shows that there are infinitely many exotic 4-manifolds with inequivalent genus functions.
Right.
But each of those genus functions is equivalent to infinitely many other exotic 4-manifolds.
That's right, theorem 1.6.
Okay, and that one is a little bit harder to visualize.
Yeah.
Can you walk me through that one again?
So the idea is to build on the families of exotic 4-manifolds that we've already constructed.
Okay.
We start with a collection of 4-manifolds that have different genus functions.
Okay, so we're starting with some exotic manifolds that we know have different genus functions.
Right.
Okay.
And then we know that each of those manifolds gives rise to an infinite family of exotic structures with the same genus function.
Right, from the quark twisting.
Exactly.
So what we end up with is this kind of tree structure.
Yeah.
Where each of the original manifolds is a branch.
Right.
And on that branch are infinitely many exotic structures with the same genus function.
That's right.
But different branches have different genus functions.
Precisely.
Okay, that helps me visualize it.
Good.
So it's like we have this tree with infinitely many branches.
Right.
And each branch has infinitely many exotic manifolds on it.
Exactly.
Wow, that's really amazing.
It is, yeah.
So we've seen that genus functions can tell us some things about exotic structures, but they can also be blind to certain types of exotic phenomena.
Right.
What does that tell us about the big picture of 4-dimensional topology?
It tells us that the relationship between smooth structures and topology in dimension 4 is much more subtle and complex than we might have thought.
So there's still a lot more to discover.
Yeah.
Okay, so we've seen how Yasui constructs these amazing families of exotic four manifolds.
Right.
But he also looks at how these structures are affected by operations like connected sums and boundary sums, right?
He does, yeah.
Can you tell me a bit more about that?
So he proves several theorems about the stability of genus functions under these operations.
Okay, and by stability, you mean that if we start with two four manifolds with different genus functions,
right,
and then we combine them using a connected sum or a boundary sum,
yeah,
the resulting manifolds will still have a different genus function.
Right. The difference in the genus functions is preserved.
Okay. And are there any conditions on the manifolds we're combining for this to hold?
Yes. The manifolds we're combining need to be relatively simple.
Okay. And what do we mean by simple in this context?
In this context, it means that they have trivial second homology groups.
So they don't have any of those two-dimensional holes that contribute to the genus function.
Exactly.
Okay. So if we add these simple manifolds, it's like we're not really changing the fundamental structure of the genus function.
That's right.
Okay, but then you're saying that this stability can break down if we use more complex manifolds in the connected sum or boundary sum.
Right. If the manifolds we're adding have non-trivial second homology groups, then the resulting genus function can be very unpredictable.
So it depends on the specific manifolds involved.
Precisely.
Okay, this is all really fascinating stuff.
It is, yeah.
It seems like there's still so much to learn about how these exotic structures behave under these operations.
There are definitely still open questions in this area.
Okay, well, this has been a great discussion of Yasui's results so far.
Yeah.
I think we've made some good progress in understanding this world of exotic four manifolds and their genus functions.
Right.
And now I'm really curious to learn more about exotically knotted submanifolds.
Yeah, that's a fascinating topic.
So let's move on to part 3 of our deep dive, where we'll explore those in more detail.
Okay, sounds good.
Welcome back to our deep dive into the world of exotic four manifolds. We've been exploring how quark twisting, quasi-invertible cobordisms, and the genus function can be used to understand these fascinating structures.
Yeah, and now we're going to dive into another layer of complexity.
Right. Exotically knotted submanifolds.
Precisely.
These submanifolds, they really seem to embody the strangeness of four-dimensional topology, where things can be topologically unknotted but smoothly knotted.
Exactly.
It's like we need this new lens of smooth structures to even see these knots.
That's a good way to put it.
So can you remind me how these exotic knots come up in Yasui's work?
They emerge as a natural consequence of the quark twisting construction. When we perform a generalized quark twist on a four manifold, we're not just changing the smooth structure of the manifold itself.
Yeah.
We're also potentially creating exotically knotted submanifolds within it.
So the quark twist can kind of induce a knot in a submanifold, even if it wasn't originally knotted.
Right.
Can you give me a specific example of how that happens?
Sure. Let's say we have a four manifold X.
Okay.
And inside X, we have a codimensions 0 submanifold C.
Okay, so codimension 0 means that C has the same dimension as X.
Right.
Okay.
And let's say that C is a quark.
Okay, so it's contractible and has that twisting self-diffeomorphism.
Exactly.
Right.
Now, if we perform a quark twist along C within X, we remove C, glue it back in using the twisting diffeomorphism.
Right, we get a new manifold X.
Precisely.
Which is topologically the same as X, but smoothly different.
Right.
But how does that create an exotic knot in C?
Well, the original submanifold C, when viewed within this new smooth structure of X, can become exotically knotted.
Wait, so we didn't actually tie a knot in C, but the quark twist made it knotted.
That's right.
That's pretty wild.
It is.
So is this just something that happens with quarks? Or can it happen with other kinds of submanifolds too?
It's not limited to quarks.
Okay.
Yasui shows that under certain conditions, any codimension 0 submanifold can be modified to create infinitely many exotically knotted and embedded submanifolds.
Okay, so exotic knotting is more general than I thought.
Yeah.
What exactly do we mean by exotically knotted and embedded?
So there are actually two different notions of exotic behavior for submanifolds.
Okay.
The first is exotically knotted, and that focuses on the relationship between two submanifolds within a fixed, smooth structure.
Okay.
So two submanifolds are exotically knotted if they're diffeomorphic, meaning there's a smooth map between them.
Yeah.
And they're topologically ambient isotopic, meaning We can continuously deform one onto the other.
Okay.
But they're not smoothly ambient isotopic.
So there's no smooth way to deform one onto the other.
Yeah. The second notion is exotically embedded.
Okay.
And that focuses on the relationship between a submanifold and the ambient manifold.
Okay.
So two submanifolds are exotically embedded if they're diffeomorphic, and the ambient manifold has a self-homeomorphism that takes one to the other.
Yeah.
But it doesn't have a self-diffeomorphism that does the same.
So we can't smoothly rearrange the ambient manifold to map one submanifold onto the other.
Right.
Okay, so those are the two different types of exotic behavior.
Yeah.
And Yasui is looking at submanifolds that exhibit both types, right?
That's right.
Okay, so how does he actually construct these exotically knotted and embedded submanifold? What are the steps?
He uses a combination of techniques,
Okay.
including cork twisting and attaching specific cobordisms.
Okay.
For example, Theorem 1.9 in the paper describes a general method for creating these exotic submanifolds.
Okay, can you tell me what Theorem 1.9 says?
Sure. It says that if you have a codimension 0 submanifold X of a 4-manifold Z,
Okay.
and the exterior of X satisfies certain conditions.
What does exterior mean in this context?
The exterior of X is the closure of Z minus X.
Okay.
So it's everything in Z that's not in X.
Okay, and what are the conditions on the exterior?
It has to either be a two-handle body or embed into a symplectic 4-manifold with a weakly convex boundary.
Okay, so we need those conditions to be able to create the exotic knotting.
Right.
Okay, and then how does the proof work?
The proof involves carefully modifying X using a combination of cork twisting and cobordism attachments.
Okay.
Yasui constructs a sequence of modifications that gradually introduce the exotic knotting,
Okay.
while still preserving the topological properties of X and Z.
So it's like a delicate surgery where we're carefully reshaping the submanifold without changing its overall topology.
Exactly.
Okay, and that gives us these exotic submanifolds.
Right.
So what's the significance of these results? What do they tell us about four-dimensional topology in general?
They highlight the profound differences between smooth and topological structures in dimension 4. Even simple submanifolds can exhibit very complex behavior when we consider their smooth structures.
Right.
And this has big implications for our understanding of four-dimensional topology in geometry.
Okay, it seems like there's a lot more going on in dimension 4 than we might expect.
Definitely.
So we've talked about exotically knotted submanifolds.
Yeah.
But doesn't Yasui also discuss how these exotic phenomena affect genus functions under connected sums and boundary sums?
He does.
Can you remind me what he says about that?
So he proves several theorems that establish a certain stability of genus functions under these operations,
Okay.
even when exotic knotting is present.
Okay, and what does that mean?
It means that if we start with two 4-manifolds with different genus functions,
Yeah.
and we combine them using a connected sum or a boundary sum with a simple 4-manifold,
Okay.
the resulting manifold will still have a different genus function.
Okay, and what does simple mean in this context?
It means that the 4-manifold has a trivial second homology group.
Okay, so it doesn't have any of those two-dimensional holes.
Right.
So adding these simple manifolds doesn't mess up the difference in genus functions.
Exactly.
Okay, and Yasui goes beyond that, right? He looks at more general conditions for this stability to hold.
He does, yeah. For example, Theorem 1.1c10 gives a stability result under the assumption that the intersection forms of the manifolds are non-degenerate, and either their second homology groups are torsion-free, or the subgroups associated with the cobordisms are torsion-free.
Okay, so the presence or absence of torsion in the homology groups plays a role.
Right.
This is really intricate stuff.
It is.
But it's fascinating to see how all these different pieces fit together.
Yeah, it really is.
Well, this has been an incredible journey exploring the world of exotic 4-manifolds.
It has.
We've covered so much ground. From cork twisting and quasi-invertible cobordisms to genus functions and exotically knotted submanifolds.
Right. It's been a whirlwind tour of four-dimensional topology.
What are some key takeaways you'd like our listeners to remember from our discussion?
I think the most important takeaway is that Dimension 4 is a very special place. The familiar rules of lower dimensional topology break down, and we see all sorts of new and unexpected phenomena.
Right, it's like a whole new world of possibilities opens up.
Exactly.
And we've only scratched the surface. There's still so much more to explore.
Definitely.
Well, I want to thank you for guiding us through this fascinating world.
My pleasure.
And to our listeners, keep exploring, keep questioning, and keep diving deep into the wonders of mathematics. Welcome to the Deep Dive. Today, we're going on a bit of a journey into the world of four-dimensional manifolds.
Right.
Specifically those with exotic smooth structures. We've got some really interesting source material you've given us, and I can't wait to really get into it. Now, I know we're all pretty familiar with the idea of a manifold, but when we start talking about four manifolds, things get a little tricky, right? We're dealing with spaces beyond our normal three-dimensional intuition.
Absolutely. Yeah, trying to visualize a four-manifold directly is pretty much impossible for us. But, we can use mathematical tools, analogies, things like that to try to grasp their properties. Think of it this way. Imagine a sphere, perfectly smooth. Now imagine another sphere that looks just like it, but has a different texture at the four-dimensional level. That's basically what an exotic four-manifold is. Topologically, the same as a standard four-manifold, but with a different smooth structure.
Okay, so it's like two sculptures. They look identical, but one is made of smooth marble and the other one's carved from wood.
Yeah. That's a great analogy. And these exotic structures, they have some really interesting implications for how we understand four-dimensional topology. For example, in lower dimensions, the smooth and topological categories are basically the same, but in four dimensions, they diverge like crazy.
So our intuition about smoothness, which works fine in our regular 3D world, just totally breaks down when we hit the fourth dimension. That's wild. One of the sources you sent us, constructing infinitely many smooth structures on small four manifolds, dives right into this, focusing on a particular type of four manifold. It's called a two-handle body, and uses these things called generalized quarks to create exotic structures. Can you tell us a little bit more about these quarks and how they work?
Sure. So basically, a generalized quark is a four-manifold with a boundary that has some special properties. You can twist it inside of a larger four-manifold, and this twisting, it changes the smooth structure of the larger manifold without changing its topology. It's kind of like if you swap out a puzzle piece for a slightly different version. The big picture is the same, but the details are different.
So they're like these special keys that unlock all these hidden exotic structures inside four manifolds. But how do we even know these exotic structures exist? I mean, how do you prove that when you're talking about spaces we can't even picture?
Well, that's where the beauty of mathematical proofs comes in, right? The source material sets up this very rigorous framework for proving these exotic structures exist. They use techniques from algebraic topology and differential topology. For example, theorem 3.6 in the paper describes a method for constructing these pairs of exotic four manifolds using specific self-diffeomorphisms. It's pretty complicated, but it basically comes down to carefully attaching these generalized quirks and then using the properties of the resulting smooth four manifold to show that it's different from the original.
So it's like this complex four-dimensional surgery, carefully cutting and pasting these quarks to create something entirely new. It's amazing how mathematicians can work with these super abstract ideas and prove such concrete results.
Yeah, it really speaks to the power of mathematics to reach into these realms we can't directly perceive. The paper also shows just how many of these exotic structures exist. It's surprising. Theorem 4.1, for instance, says you can take A and Y four-dimensional two-handle body and turn it into a generalized quark of infinite order.
Hold on, infinite order, what does that even mean in this context?
It means you can twist that quark an unlimited number of times, and each twist could create a new exotic four-manifold. We're not talking about a few exotic structures here. We're talking about maybe infinite variations within just one topological type. So yeah, that's a lot of exotic four-manifolds.
Yeah, wow, that's a lot to think about. So it's like each two-handle body is this treasure chest full of exotic structures just waiting to be unlocked by these quarks. But how do mathematicians actually build these exotic four-manifolds? The paper mentions something called W and W plus operations. What are those about?
Basically, there are ways to surgically modify these two handle bodies. It's like carefully cutting and pasting parts of the four-manifold guided by these W operations. By applying specific sequences of these operations, along with some quark twists, mathematicians can create this huge variety of exotic structures.
So it's like having a set of four-dimensional building blocks and a set of instructions for putting them together to create all these different exotic creatures. Can we go over the definition of WM and W plus operations in detail from definition 3.1?
Sure. So let X be a smooth four-manifold. Let $T$ and $T$2 be two embedded tori in X with trivial normal bundle, and suppose there exists an embedded sphere S with trivial normal bundle in X such that C of T1, T plus level 1, and C dollars for any other embedded tor C dollars with trivial normal bundle. Blow up X at the intersection point of $T$ and dollars, and then blow up again at the intersection point of the proper transform of T$, and T$2, and the exceptional sphere of the first blow up. This operation is denoted xt1 t2 dollar. The operation dollar plus xt1 t2 s dollar is defined as the inverse of the operation w xt1 t2 t2 s dollar. It is important to note that the existence of the embedded sphere sided dollars with the specified intersection properties is crucial for the definition of the Chilvers operations. This sphere essentially controls how the toric T-dollar and T-dollar are modified during the blow-up and blow-down processes. The sign of the intersection numbers of Zollars with T-dollars and T-dollar2 determines whether the operation is a dollar-dollar or a dollar-plus operation.
That's a lot of steps. But I think I'm getting the picture. It's amazing how these operations let us change the structure of the four-manifold in such a controlled way. It's like a sculptor carefully chiseling away at stone to reveal a hidden form inside.
Exactly. And the beauty of these operations is that they give us a way to systematically generate a bunch of exotic structures. Theorem 3.4, for instance, proves that by combining these WI and W plus operations with Cork twists, you can make as many exotic four-manifolds as you want within a given family. It's like we have a recipe for baking exotic four-manifolds, with each ingredient and step carefully chosen to get a specific result.
So it sounds like we've got these genus functions measuring complexity, Corks twisting things up, and W operations letting us surgically modify four manifolds. It's a lot to keep track of. What's the main takeaway here?
The main takeaway is that the world of four-dimensional manifolds is way more complex than our three-dimensional intuition would suggest. The fact that these exotic four manifolds exist challenges how we think about smoothness, and it opens up a whole new world of possibilities for understanding space and shape.
It's like realizing that the universe is stranger than we imagine. It's stranger than we can imagine.
Exactly.
But let's not get ahead of ourselves. Before we jump to part 2, can we dig a little deeper into how they actually prove Theorem 3.4? I'm curious about how they demonstrate the existence of all these different exotic structures.
Sure. The proof uses this really clever construction with a specific family of four manifolds called two-handle bodies. The authors start with a kind of base two-handle body and then systematically apply sequences of more operations and carefully chosen Cork twists. Each sequence produces a new four-manifold that's topologically the same as the original, but has a different smooth structure. The trick is to show that these different smooth structures are actually distinct from each other.
And how do they do that? How do they prove that these structures aren't just different in some trivial way?
They use the properties of those Cork twists and the operations. Remember, each Cork twist can introduce a unique twist to the smooth structure. By carefully selecting the Corks and the sequence of operations, they can make sure that each resulting four-manifold has its own unique combination of twists, which makes its smooth structure distinct from all the others. It's like giving each four-manifold its own fingerprint based on how it was built.
That's really clever. So it's not about randomly doing these operations. It's about carefully orchestrating them to create very specific and unique smooth structures.
Right. The proof of Theorem 3.4 really shows how powerful it is to combine geometric intuition with these rigorous algebraic techniques when you're exploring the world of four-dimensional manifolds. It highlights the fact that even within a seemingly simple family of manifolds, there can be an incredible diversity of smooth structures hiding beneath the surface.
It's like discovering a hidden garden full of all these exotic and unexpected forms, right there in the familiar territory of four-dimensional topology. Before we finish up part 1, can we take a look at Theorem 3.5, which talks about the existence of an invertible homology cobordism?
Absolutely. Theorem 3.5 is really important to this whole construction. It says that for any three-manifold dollars that you can embed in 393 hours and bounds a Stein four-manifold, you can find an invertible homology cobordism, which we'll call a dollars from all to itself. And this dollar has some special properties. It can be embedded in a five-dimensional space, which is $3 in dollars and $1 in dollars without adding any holes. And any diffeomorphism of Y can be extended to a diffeomorphism of dollars. So we've got this four-dimensional cobordism, W, connecting dollars to itself.
So this cobordism acts as a bridge, letting us transfer diffeomorphisms from the boundary three-manifold to the inside four-manifold. And because it's invertible, we can go back and forth without losing any information.
Precisely. And the cool thing about this theorem is that it works for a lot of different three-manifolds. Any three-manifold that you can embed in the four-sphere and bounds a Stein four-manifold, which has some nice geometric properties, will satisfy the conditions of Theorem 3.5. This opens up a lot of possibilities for constructing exotic four-manifolds.
This is also fascinating. We've covered a lot in this first part of our deep dive, from the basics of exotic four-manifolds to the intricacies of generalized quarks, W operations, and invertible homology cobordisms. It's clear that this is a really deep and complex field of study.
Picking up where we left off, I think it's amazing how these abstract mathematical ideas can have such big implications for understanding the universe. For example, the fact that exotic four-manifolds exist challenges our basic assumptions about space and time.
Totally. And the paper really explores these implications. One thing that stood out to me is the idea of stably exotic four-manifolds. Can you explain what that means? I think it comes up around theorem 1.1 day.
Sure, so a stably exotic four-manifold is one where that exotic structure sticks around even when you combine it with another manifold. It's like its exotic nature is so deeply ingrained that you can't just smooth it away. Theorem 1.17 specifically talks about exotic four-manifolds that have Stein structures. Stein manifolds are a special kind of complex manifold with really nice properties. What's interesting is that according to Theorem 1.17, when you combine these exotic Stein four-manifolds with other Stein manifolds, the resulting manifold is still exotic. They do this through a process called a boundary sum.
So even when you merge them with these well-behaved Stein manifolds, they hold on to their exotic twist. It's like their exoticness is contagious. Can you clarify what a boundary sum is?
Of course. Imagine you have two manifolds, each with a boundary. A boundary sum is basically a way of gluing them together along their boundaries to make a new manifold. It's like taking two pieces of fabric and sewing them together along the edges.
Oh, okay, that makes sense. So here, we're stitching together an exotic Stein four-manifold with another Stein four-manifold, and the result is still exotic. That really shows how strong these exotic structures are, doesn't it? But let's switch gears for a second and talk about another cool concept from the paper, exotically knotted submanifolds. I think this is explored around Theorem 1.9.
Yes. These submanifolds are like puzzle pieces that fit topologically but not smoothly within a larger manifold. It's as though they're knotted in some higher dimensional way that we just can't fully visualize. And Theorem 1.9 shows just how common these exotically knotted submanifolds really are. It states that under certain conditions, you can take almost any codimension 0 submanifold of a four-manifold and turn it into an infinite family of exotically knotted and embedded submanifolds.
Wait, so you're saying that inside a single four-manifold, there could be countless submanifolds that are topologically the same but smoothly different. That's wild. Can you give us an example to illustrate this concept?
Sure. Let's take the four-sphere, a standard four-dimensional sphere. Imagine a three-dimensional sphere embedded in this four-sphere. Topologically, this three-sphere can be embedded in a simple way. But Theorem 1.9 tells us we can also embed it in infinitely many other ways, each one giving us a submanifold that's topologically a three-sphere, but smoothly distinct from the standard embedding. It's like taking a string and tying it into a bunch of different knots. Each knot represents a different smooth structure for the same basic shape.
So it's like we're taking a simple object, like a three-sphere, and revealing a hidden world of complexity by putting it in a higher dimensional space. It's like finding a secret garden in a familiar landscape. Can we go over Corollary 1.10, which talks about four manifolds containing infinitely many exotically knotted submanifolds?
Absolutely. Corollary 1.10 says that every smooth four-manifold, whether it's orientable or not, will contain infinitely many smoothly distinct but topologically isotopic embedded three spheres. This means that if we have any smooth four-manifold X and any embedding 5 DOS or 3 to X3, we can always find infinitely many other embeddings S3. Each S3 is topologically isotopic to 4S to 3, meaning there's a continuous family of embeddings from 5S3 to 3, but each S3 is solely different from 4S3, meaning there is no diffeomorphism of sex3 that can take 5S3 to 3 to S3. And importantly, all these DS3 are also smoothly distinct from each other, meaning no diffeomorphism of 6 spheres can take S3 to 2 or 3 if A and DS3 are different. This corollary really reinforces the idea that exotic embeddings of three spheres aren't just found in special four manifolds, but they're everywhere in four-dimensional topology. It highlights the big difference between the smooth and topological categories in dimension 4.
Wow, it sounds like the fourth dimension is like the Wild West, where our intuition from lower dimensions just doesn't apply. But before we move on, can we rewind a bit and go over the proof of Theorem 1.9? I'm curious about the math they use to create these exotic knots.
Of course. The proof cleverly uses several key ideas we've already talked about. It starts by looking at a codimension 0 submanifold, which we'll call X, inside a larger four-manifold, Z. Remember those generalized quarks we discussed earlier? The proof uses the fact that in certain situations, the space surrounding X within Z can be transformed into a generalized quark.
So you're saying we take the space around X, twist it up with a cork, and then use that twisted exterior to make exotically knotted versions of X itself.
Exactly. And the conditions needed for this transformation aren't that strict. For instance, the exterior of X just needs to be a two-handle body, which we talked about earlier as being a very common type of four-manifold.
Ah, so we're tapping into that same cork twisting magic from before, but now we're applying it to create exotic knots within submanifolds. That's brilliant.
It is. And the proof beautifully demonstrates that by twisting the exterior of X in different ways, using different corks, you can create infinitely many different smooth structures on X while still keeping it topologically embedded within Z.
It's like playing a game of four-dimensional knot tying, where each knot represents a different smooth structure. But this isn't just a game, is it? These exotic knots have real implications for how we think about the universe.
You're absolutely right. The fact that these exotically knotted submanifolds exist highlights this deep and often counterintuitive connection between smoothness and topology in four dimensions. They show that even within one four-manifold, there can be a huge variety of hidden structures. And as you mentioned, this might even have connections to the real world, especially in theoretical physics.
Yeah, for example, some physicists think that the universe could have extra hidden dimensions. And if those dimensions contain exotic structures like the ones we've been talking about, it could really shake up the laws of physics.
For sure. The whole idea of space-time, which is the foundation of how we understand the universe right now, is closely tied to the smooth structure of a four-manifold. If space-time itself has exotic structures, it could lead to completely new and unexpected physical phenomena.
It's like realizing that the universe is not only weirder than we think, but it's weirder than we can even imagine. But hold on, we still need to talk about those other theorems about exotically knotted submanifolds in codimension 1. Theorem 1.11, for instance, talks about how to modify closed three-manifolds into exotic knots inside a larger four-manifold.
Yes, and what's particularly interesting about this theorem is that it uses homology cobordisms, which are like four-dimensional tunnels connecting different three-manifolds without changing their homology groups. Those homology groups are these algebraic objects that tell us about the holes in a space.
So instead of twisting the exterior of the submanifold, like in Theorem 1.9, we're using these homology cobordisms to create exotic knots. Can you explain these homology cobordisms a bit more?
Absolutely. A homology cobordism between two three-manifolds, let's call them Y1 and Y2, is a four-manifold W with a boundary. The boundary of W is the disjoint union of Y1 and Y2, and when you include Y1 and Y2 into W, it creates isomorphisms on their homology groups. Basically, W fills in the space between Y1 and Y2 without making any new holes. Imagine connecting two rooms with a hallway that doesn't have any doors or windows to other places.
Ah, I see. It's like creating a smooth transition between these two three-manifolds without changing their basic topological features. And Theorem 1.11 tells us we can use these homology cobordisms to knot up our three-manifolds inside a bigger four-manifold.
Exactly. Theorem 1.11 says if you have a closed three-manifold embedded in a four-manifold and the space outside its tubular neighborhood meets certain conditions, then you can use homology cobordisms to modify that three-manifold into tons of exotically knotted submanifolds.
And are the conditions on the exterior similar to the ones in Theorem 1.9? Like, does it need to be a two-handle body or embeddable in a symplectic four-manifold?
Yeah, the conditions are similar. The space outside the three-manifold's tubular neighborhood needs to have a specific structure, so we can use the properties of homology cobordisms to make those exotic knots.
So it's like taking our three-manifold on a trip through these four-dimensional tunnels, and when it comes out the other side, it's all knotted up in an exotic way inside the bigger four-manifold.
Pretty scenic and transformative journey. And the corollaries to Theorem 1.11 give us even more interesting insights. Corollary 1.12, for example, says that if you can embed a closed three-manifold into the four-sphere, then every four-manifold will have an infinite number of exotically knotted submanifolds that are homology cobordant to that three-manifold.
Wow, so being able to embed a three-manifold into the four-sphere has big consequences. It's like a seed of exoticness that you can plant in any four-manifold. Can we unpack Corollary 1.12 a little more?
Sure. What Corollary 1.12 basically says is that if we have a three-manifold, let's call it Y, that can be embedded into the four-sphere, then any other four-manifold, let's call it X, will contain a bunch of exotically knotted submanifolds that are homology cobordant to Y. Basically, there are infinitely many ways to embed a three-manifold that's homology cobordant to Y into X, and each way gives you a smoothly distinct submanifold. This shows that exotic knotting isn't just something that happens in special four-manifolds, it's a common feature of four-dimensional topology.
That's amazing. And I imagine Corollary 1.32 takes this idea even further, pushing the boundaries of exoticness.
Exactly. Corollary 1.13 shows that there are infinitely many different homology cobordism classes of 3 manifolds. And for each class, every 4 manifold will contain an infinite number of exotic knots that are diffeomorphic to a representative from that class.
So we're talking about a truly massive network of exotic structures here, spanning different dimensions and topological types. It's like this hidden mathematical tapestry woven together with smoothness and knot theory.
I like that analogy. And remember, this whole discussion of exotically knotted submanifolds is just one part of the larger world of exotic 4 manifolds. We still have a lot to learn, but one thing's for sure, these exotic structures show us how rich and complex 4-dimensional topology really is.
It's like we're getting a glimpse into a vast and unexplored territory where our ideas about shape and space are constantly challenged. But to navigate this territory, we need the right tools. We've talked about genus functions and Corks, but there's another important concept we need to discuss: quasi-invertible cobordisms. Section 6 of the paper dives into this topic. Can you tell us about these quasi-invertible cobordisms and why they're important for understanding exotic 4 manifolds?
Of course, quasi-invertible cobordisms are like these flexible 4-dimensional connectors that let us join and modify 4 manifolds in a way that keeps certain key properties intact. Unlike invertible cobordisms, which are more like rigid bridges between 3 manifolds, quasi-invertible cobordisms have more freedom to move and twist.
So they're like invertible cobordisms with extra flexibility. How does that help us study exotic 4 manifolds?
Remember how we talked about attaching cobordisms to 4 manifolds to create new structures? Well, the flexibility of quasi-invertible cobordisms lets us attach them while still keeping control of things like the genus functions and other important properties. This is really important because we use those properties to distinguish exotic structures.
So these quasi-invertible cobordisms let us surgically modify 4 manifolds without messing up the delicate balance that defines their exoticness. They're like specialized tools for working with these 4-dimensional structures.
Exactly. And the definitions in Section 6 give us a foundation for understanding these cobordisms. For instance, Definition 6.1 introduces the idea of a quasi-product cobordism, which is basically a 4-manifold that can be transformed into a product cobordism by doing surgery on a bunch of embedded circles.
So it's like we're allowed to smooth out the cobordism by doing these surgical modifications. Can you explain what smoothing out the cobordism means and why it's so important?
Sure. When we say smooth out a cobordism, we mean changing its structure through a series of well-defined surgeries. In the case of a quasi-product cobordism, these surgeries involve removing tubular neighborhoods of embedded circles and replacing them with simpler structures. This process simplifies the cobordism without changing its important topological features, making it easier to analyze.
That makes sense. Simplifying the cobordism helps us focus on its key features without getting lost in the details. It's like simplifying a complex equation to its most basic form. Can we look at definition 6.1, which formally defines a quasi-product cobordism?
Absolutely. Definition 6.1 says, a cobordism, $1, is called a quasi-product if it is diffeomorphic to a cobordism obtained from $y dollars, y0 dollars, y0, y0 dollars, under y0 gun dollars by a finite sequence of surgeries on pairwise disjointly embedded circles in int to yy times 0, $1. So a quasi-product cobordism can be created by starting with a simple product cobordism and performing a series of surgeries on circles embedded in its interior. These surgeries involve removing a tubular neighborhood around each circle and gluing in a filling that changes the topology of the cobordism. Basically, they modify the structure of the cobordism in a controlled way, allowing us to build more complex cobordisms while still keeping certain desirable properties.
This is so fascinating. It's like we're starting with a simple building block and using these surgical modifications to create something more intricate, all while preserving its essential properties. But how do we make sure these changes don't mess up the properties we're trying to keep?
Well, that's where carefully choosing the surgeries and analyzing the cobordism's invariance comes in. The paper gets into these technical details in Section 6, creating a framework for understanding how different kinds of surgeries affect the properties of quasi-invertible cobordisms.
Sounds like a delicate balancing act. We're trying to add complexity while still keeping certain key features intact. Why is this so crucial when it comes to exotic 4 manifolds?
It's crucial because those key features, like the genus function, are what we use to distinguish exotic structures. Quasi-invertible cobordisms give us a way to manipulate 4 manifolds without messing up these important indicators. This lets us create new exotic structures and analyze their properties precisely.
It's like we have this special toolkit for exploring all the nuances of exotic 4 manifolds. Can we take a look at some of the lemmas and propositions that go deeper into the algebraic and topological properties of quasi-invertible cobordisms and how they are used to study exotic four manifolds?
Of course. For example, lemma 6.2 states, a cobordism, weight value y1 baller, is a quasi-product if and only if the inclusion map T dollars y hook right ROW induces an isomorphism on homology. This basically gives us a topological way to define quasi-product cobordisms. It says that a cobordism is a quasi-product only if the inclusion map from its bottom boundary component into the cobordism creates an isomorphism on homology groups. This means the cobordism doesn't make any new holes in the space, preserving the topological structure of the boundary it's attached to.
Oh, I see. So we're checking if the cobordism adds any new topological features. If it doesn't, it's a quasi-product. This seems really useful for understanding these cobordisms.
Exactly. These lemmas and propositions provide the mathematical groundwork for working with and analyzing quasi-invertible cobordisms. They let us prove that the things we do to four manifolds using these cobordisms are well defined and don't mess up the properties we want to study.
It's like building a mathematical framework, piece by piece, so we can explore four-dimensional topology with more and more confidence and sophistication. These quasi-invertible cobordisms seem like incredibly versatile tools for exploring this exotic landscape.
They really are. And the paper goes on to show just how powerful they are in later sections, where they're used to prove some key theorems about genus functions and exotic structures.
Welcome back to our deep dive into exotic four manifolds. We've been exploring these crazy spaces and all the mathematical tools that help us understand them. We've talked about genus functions, those twisting quarks, and those flexible, quasi-invertible cobordisms, which are kind of like specialized surgical tools.
And now in this last part, we'll see how all these tools come together to give us a deeper understanding of how genus functions behave, especially when we start attaching these quasi-invertible cobordisms. Section 7, Genus Functions and Quasi-Invertible Cobordisms, has some key theorems and corollaries that really shed light on this connection.
Great. So we've got our four-manifold toolkit ready to go. Let's see how we can use it to figure out what happens to genus functions when we start attaching these quasi-invertible cobordisms. Theorem 7.1 seems like a good place to start. It says that if you attach a quasi-invertible cobordism to a four-manifold, the genus function stays the same. That sounds pretty fundamental.
Yeah, it's really a cornerstone of this whole framework. The proof is pretty complex, but the basic idea is this. When you attach a quasi-invertible cobordism, you're adding a piece that you can smooth out using surgery. This smoothing process makes sure that the overall topology of the four-manifold doesn't change too much, which in turn means the genus function doesn't get messed up.
So it's like doing delicate surgery on the four-manifold, carefully grafting on this extra piece without changing its basic structure. But how can we be sure that the genus function really stays the same? The proof must use some pretty advanced arguments.
You're right. The proof uses a mix of algebraic and geometric techniques. It involves creating this specific sequence of diffeomorphisms and inclusions and carefully keeping track of how each step changes the homology groups and the genus function. It's a great example of how algebraic topology gives us a precise way to describe these geometric operations.
So we're using the power of algebra to translate our geometric intuition into statements that we can actually verify. It's really cool how these two seemingly different areas of math work together in this proof. But can we break down Theorem 7.1 a little bit more? What does it actually tell us about the genus functions?
Sure. Theorem 7.1 essentially says that if you have a smooth, closed, connected-oriented four-manifold, we'll call it X, and a quasi-invertible cobordism, WYYY, with B by dollar is the boundary of $6, then if you attach dollars to 6 along, the genus function of the resulting four-manifold is the same as the genus function of $6. So basically, attaching a quasi-invertible cobordism doesn't change the genus function.
Okay, I think I'm starting to get it. So we're saying that even after we attach this potentially complicated cobordism, the way we measure the complexity of surfaces embedded in the manifold stays the same. It's like the genus function is this tough invariant that can handle these surgical modifications.
Exactly. And this invariance is super important because it means we can use the genus function as a tool to distinguish between different smooth structures. Remember, exotic four manifolds are topologically the same, so we need these subtle invariants to tell them apart.
Right. It's like trying to tell the difference between two butterfly species that look almost identical. You have to zoom in on the patterns on their wings to see the difference. But here, we're using the genus function as our distinguishing feature.
Exactly. And theorems 7.7 through 7.9 give us even more tools for this delicate task of distinguishing exotic structures. They tell us that under certain conditions, if we have two four manifolds with genus functions that are algebraically different, this difference will stick around even when we do connected sums and boundary sums with a specific kind of four manifold.
So if we have two four manifolds with different genus functions, and we combine each of them with these special four manifolds, the resulting combos will still have different genus functions.
That's right. This stability of the differences is really important because it means we can build more and more complex four manifolds while still keeping track of the differences in their smooth structures. It's like we're building this hierarchy of exoticness with each level based on the one before it.
It's incredible how all these theorems and corollaries give us this sophisticated way to understand and manipulate exotic four manifolds. They let us explore four-dimensional topology with amazing precision. But I can't help but wonder, what does all this mean in the bigger picture? We're talking about objects that we can't even visualize. What can these exotic structures tell us about the universe we live in?
That's a deep question, and one that mathematicians and physicists are still trying to answer. On the one hand, these exotic structures exist in 4 dimensions, and we only experience 3 dimensions in our daily lives. But some theoretical physicists think that the universe might have hidden higher dimensions that we can't directly see.
So could these exotic structures be hidden within the fabric of space-time, influencing the laws of physics in ways we don't yet understand?
It's a really interesting possibility. The very idea of space-time, which is at the heart of our current understanding of gravity and the universe, is closely connected to the geometry of a four-manifold. If space-time itself had exotic structures, it could lead to entirely new and unexpected physical phenomena, things we haven't even imagined yet.
It's mind-blowing to think that these abstract mathematical ideas could have such a huge impact on the real world. It's like we're getting a glimpse into a hidden part of reality, a dimension where the rules of space and time are bent and twisted in ways that go against our intuition.
And this is just the beginning. The study of exotic four manifolds is a pretty new field, and there's still so much to explore and discover. Who knows what other strange and amazing structures might be out there in the vast landscape of four-dimensional topology.
It's both exciting and humbling to realize we've only just started to explore this fascinating and mysterious world. It's a testament to the power of human curiosity and the endless possibilities of math. But we've covered a lot in this deep dive, and I feel like I've gained a whole new understanding of space, dimension, and how incredibly powerful math is for unlocking the secrets of the universe.
It's been great exploring these ideas with you, and for our listeners who want to dig even deeper, I highly recommend checking out the sources we've talked about today. There's a ton of knowledge out there just waiting to be discovered.
Absolutely. And who knows, maybe some of our listeners will be inspired to make their own contributions to this exciting field of research. Until next time, stay curious and keep your minds open to the infinite possibilities of the mathematical universe.